So I strongly suspect there should be questions from last Tuesday, because I threw some extraordinarily complicated and involved stuff at you. Okay, so I wasn't expecting you to get it all. I was kind of trying to expose you to these are the issues. It's actually very simple. There's a simple set of rules, but they're complicated in the sense that this is not what you naturally think of, and this is kind of advanced stuff. So, are there any questions? Yes.
In your exercises that you provide, exercise number 2.
Yeah.
Can you open it actually?
I'll try. Hang on a second. I just remember where I am. Number 2?
Yeah.
Oh, stop it.
So what does that R, the lowercase r, mean in front of each command? Is it like a failed attempt to make an assignment, or is it just on purpose to kind of create the error?
This is an annoyance that I did not see this. This is an annoyance of Markdown, converting Markdown file to an HTML document.
Okay. So it wasn't intended.
This is not intentional. Thank you very much. That would be all of those would be syntax errors. Okay. No, sorry. This is Markdown is extraordinarily annoying. Markdown as a way of structuring text is super convenient until it's not, and then all of a sudden it starts getting very annoying for those of us who use more flexible systems. That's all. This R is a complete typo.
Well, it kind of serves the purpose of just making the point of what you said, that how R would evaluate it. First, it doesn't look at the plus first. It looks at that R, finds an error there, and then just aborts.
Once R finds an error in any part of the text that you're giving it, it basically abandons ship and fails. Okay, and again, part of this is if you don't. One of the ways of testing this, and again, you don't need to. Most users will just go, oh, that's a syntax error, off we go, and they change the syntax. But if you go, I don't know if that's a syntax error or if it's an error after it's been parsed. One of the tricks to this is just take that text and parse it. Call parse text equals, and put the text in a string, and if it comes back and says, yep, I parsed that, then the error is at runtime, not at parse time. And that's one of the reasons I was showing you parse. You rarely ever need that, but if there's something, but some people do have extraordinarily cryptic, long commands, and it takes a while to actually look at them and say, where is the syntax error? Okay, so but sometimes just parsing it and actually having the parser explicitly do it gives you a little bit more control. So sorry about those R's. If you remind me at the end of this, I will go back and cajole it into fixing this. Thank you. Any other questions? Yes?
So just a question about the environments and the relationship of the environments to their parent and the search path. So is
yeah. Sorry. Just before, genuinely, if you understand, I had a conversation with Matt, our postdoc here, and Clark, one of my PhD students, who works on the language kind of stuff like this, and we were having this great discussion yesterday. It's super complicated. Okay, I actually drew a picture of it last night. So if you get this. The way you understand this is incrementally. Don't try to understand it all in one go. Okay, I'm just throwing it out there as it is knowable. I didn't get a chance to scan this. This is a picture where you actually have, this is your call stack, and over here is all the parent environments, okay, of the functions and the call frames, or the parent environments of these call frames. And implicitly in here is another thing, which is the search path. So you've got multiple paths going on here. So it's very complicated. So, sorry.
Yeah, so I guess I assumed that the parent of an environment was something that's not dictated by its position in the search path. But something in the notes made me think that maybe it is simply that if you reordered items in the search path, that they would then have different parents, that it maybe it's just a link between. Does that make sense? So if you order the search path, do those elements now have different parents. And I wouldn't have thought so.
Yes, the answer is absolutely yes.
Okay.
In the search path, they have different parents. So I'm going to get myself into a slightly tricky sort of part. And by the way, I apologize to other people who have very little sleep. I got very little sleep yesterday. I know there are other people in the room who got even less sleep, who have babies and stuff like that. But as Pamela was saying, it's all relative to my baseline. So if I say something that doesn't seem to make sense, please let me know. I'm very tired. Okay. There's an implementation issue here, and this was alluded to earlier on Tuesday. That how come an environment doesn't have two parents? Because it looks like it does, and the answer is it kind of does, but in the implementation they do not have two parents, and this is what makes life work. But basically, in the search path, this is always the global environment. Okay, this is your global environment, and it's very, 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 very hard to have that not be the first element in the search path. You can do it, but you can't. Okay. But then as you type library, and if you don't specify the position argument, it goes into the second place. So when we have a search path that looks like this, and eventually we end up at base. Okay. Again, these are all environments. This is where variables are found. We look up symbols in these environments. Okay. We're talking about environments here. This is a package environment. This is for packages, typically. We'll just say that this is the stats library. And when I type library of XML, okay, of the XML package, by default, it now goes in here. And what this does is it actually sticks a new environment in here containing all of the exported variables from this XML package. And it makes the parent of this new environment this guy here. Okay, so now this guy's parent becomes this. This guy's parent is still this, but this guy's parent becomes the new XML package. So we do move everything around. Now, one of the complexities is, so this here is the search path. Again, I'm glad to see many of you came back. I wasn't sure everyone would. As I say, I was actually throwing complicated stuff out, but as I say, not expecting you to get this. So if you don't understand this, that's, don't worry about it in the slightest. But just try to grab hold of some terms. So this is the search path part of the world. Okay, I did talk about this thing here, and this is the figure I held up. They're very small. Remember, we actually call scatter.smooth. Okay, and then that called XY coords, and I kind of ad-libbed. I sort of told you what was going on. I actually looked at it yesterday and go, oh, it's even richer than I thought. Oh, this is much more fun. And then we ended up down here because we actually had a call. We had scatter.smooth, and I'm going to make it simpler. It was actually to empty cars on empty cars, and I'm going to make it very simple of C of 1 and 2. Okay. So what's going to happen, and what actually happened is we called scatter.smooth. We got a call frame, which is an environment. Okay, we create a new frame for each call to scatter.smooth. In this call, we open this frame. That guy calls XY coords. That gets its own frame, and then through lazy evaluation, we actually have to go back and evaluate this thing. So this is the call to square bracket with MT cars as the first argument, and the second argument is empty because we got a comma here, and then we ended up with C of 1 and 2, and this gets even richer if we want to go. Now, the parent environment here, and the parent environment here, and the parent environment here are different from the search path altogether. Okay, that's the weird thing. That's where you go like, hang on a second, how can it be in two places at the same time? Trust me. Okay, and then the parent environment of this is the actual environment of scatter.smooth, which is in the stats package. So this is stats. And then that has another one over here, which is actually called imports. And then we get to base. Okay. And then over here, actually, this one actually turns out to be in the graphics. This turns out to be in the graphics package, which also has another imports, and then it gets to base. And then magically, and again, if you understand this stuff, come and join us in R, because we need people who understand this, who actually can play this game. Then this guy magically has to know where empty cars is. And if you remember, this is a promise. We call these promises. It came in the call here. It got assigned to the variable x here. We don't evaluate it until it's needed. It's needed here, but it's still not needed. So it's a promise here. Then it comes down to here. Now we actually finally need it. And when, in a promise, I told you basically we take the command, this call object, but we also grab the environment in which it makes sense, which is, at this point, the top level command line. So it grabs the global environment, and that's where it can find empty cars along the search path. So this guy is actually the search path. Okay? But these guys are all packaged in. The search path for these guys are related to the packages. Does that make sense? So the search path is definitely where we look for, when I type the command 1 + 2, we look for plus along the search path because it's at the top level command. When I type scatter.smooth of empty cars, it's at the command line, so we look for scatter.smooth, we find it in the stats package. When we evaluate the code in scatter.smooth, we do it in the call frame, and its parent environment, and so forth, which is different from the search path.
Right, so at that point, we're no longer using the search path. I think that's where the confusion was for me, is that
it's very
part of the parenthood seems completely independent of the order of the things in the search path.
Obvious and good reason, and it's not obvious, but it's but it is when it doesn't work and you attach a package that has xy.coords that does something entirely different, and that will be very bad news. But because when the person who wrote scatter.smooth, you made a call to xy.coords, they knew which one they were calling. Okay, and we could have written scatter.smooth in here. We could have written this down as xy, so there's a call xy coords, x and y, and xlab and ylab. We could have actually put this in as saying, oh, it's in graphics. Okay, we could have said, no, I'm telling you where it is. This is an annoying language if I have to be really, really, tell us where everything is. So we'll talk about this on next week. When we write a package, you basically sort of say, look, these are the other packages on which I depend, and I'm going to kind of seal this now so that nobody can screw around with the search path and make my code behave horribly. We get a lot of email. From yesterday, we got one great piece of email saying, I found a bug in R. Well, no, you found a bug in your code. They gave us an 800-line call stack in C. So it was just basically do the same thing over and over again. It's like, this is all to do with what you have attached. So I mean, imagine if your code, if our code depended on what was in your search path, and there's 10,000 packages, this would be a nightmare. So that's why this is very elaborate. But let me just say, in here, we are searching this chain of environments based on their parents and their ancestors. Here, we are searching a chain of environments. Here, we're searching a chain of environments. It's a different chain. But the way to think about this is we're always searching a chain. And you can always find that chain, okay? Except for the last one. Except for this one down here. This promise business, you can't quite access easily. But it is the same logic. And that's all I'm trying to get across, is that logic. Okay, does that make sense?
I think so. Yeah. I think so. Can you state that? So
please.
In the search path, the stats object, that element has the parent within the context of the search path. It's the next item to the right.
Yeah.
But if you called a function that was within the stats package, then you would be in a context in which it has a different parent structure. It has the one that was defined at the time that package was put together.
Yes.
Okay.
Absolutely. That's that. Okay. And it's always this. And this is a nice example because we actually use both. This one here, when we actually have to evaluate the square bracket of empty cars, we're actually going back to the search path, okay, because it's at the top level. So we are now using the search path for this guy, okay, because otherwise we wouldn't be able to find empty cars, okay, or the square bracket, but for all these other guys. But it's the same thing. We start from whatever environment it was, and then walk that guy.
The detail why the promise is different.
Why it's not different. Sorry, let me just say it's not different at all. We know where to start looking, and then we look from there. So from the promise, we start looking at the environment. The only reason I'm saying it's different is if I go into the debugger here and I say stop here, and then I say sys.frame or sys.frames, I can look at all the frames, and that is the call frame, and I can look at their parents. I can't remember, but I don't think it's directly accessible to get the environment of a promise. That's all. That's the only reason I'm saying it's different. It's very hard to reach in to a promise. At the R prompt, it's hard to reach into a promise and grab the environment. It is doable. I can do it, but you're talking to C code at this point, so I can't remember that you can actually get it. Okay, that's the only reason I'm saying it's different. But the actual computation is identical. It's grab the environment and start walking its parents. Okay, look in that environment for empty cars, didn't find it, then start walking the parent and its parent and so on. But that's
Empty cars is in base. It's just going to walk down.
Ha! It's not in base.
Okay, no.
It's on the search path.
It's on the,
It is on the search path.
but not in base.
It's not on the base. Yeah, and we could use find to actually see where it is. But go on. You were.
Just that basically it's going to go for the third square you've drawn that particular search path and then go and find empty cars there.
Yes, exactly. And it just so happens that because we gave this command, scatter.smooth, at the prompt, then that means that we're supposed to start looking at the global environment. And the global environment is the first element of the search path. That's why. If I had given this, if you had written a function, again, this is kind of, again, please, if you don't understand this stuff, that's okay. It really is absolutely fine. Okay, we're going to go on to easier stuff. But it is helpful just to be. I find it helpful to be at least aware of these things, so that you realize there may be something I should think about when something doesn't work. As I say, when some people say I found a bug in R, it's like, no, it really is your code. Okay, okay. I was just reading something last week. Somebody actually wrote a blog that says that it's always, novice programmers always say, I found a bug in Java, I found a bug in C, I found a bug in some other piece of code like R, whatever. And it's always their own code, okay? Fine, okay. He actually found a bug not in Java or R or a compiler. He found a bug in the chip. That's seriously unusual. Okay, like an actual hardware piece of an instruction doing something different than it's supposed to do. It's like, oh, good grief, But that is so rare. Okay, that's the absolute extreme. Okay, it's nearly always your code. Anyway, but so there, and therefore it's useful to try to figure out why. That's why I'm telling you about this stuff. But you don't have to understand it fully to use R whatsoever. Most people don't even have a clue that any of this exists. But if I did this, if I said f equals a function, and it takes a and b, and okay, and if you're okay, and if I call scatter.smooth of a and b, let's just say, this is slightly different from this because I've got an extra call in here. Okay, my call is going to be to f up here, and f, I will create a new call frame for f. Okay, and then I will create these parameters, the bindings with the default values, do the argument matching, and all that. All life is good. Then eventually I will get to this call here, and I will have to go find scatter.smooth. I did this at the prompt, at the R prompt, which means that this is in the global environment. F was assigned into my global environment, which means that the call frame here, its parent will be the environment of the function, which is the global environment, and therefore it will look for scatter.smooth along the search path, okay? And that's it, but it's technically slightly different. And when I put in MT cars, when I call F of MT cars, again, this is at the command line, it will call F, but MT cars will be evaluated in the global environment. F will look along the global environment, but search its own call frame first. So if I put something like A is equal to, if I do something like this, if I put X and I say X equals R norm of 100, it will find X in the call frame, not along the search path, okay? So there's one extra layer to it, but it's identical to what we've said, okay? Yes?
I have two questions, but if it takes my time, just
go on.
What happens, given that picture, what happens if we actually make a global variable assignment?
In the function or where?
No, given that picture that you have with
the right one?
Yeah, not the left. What happens if we make a global variable assignment?
Where?
So we have to do it in any of the environments.
So suppose I'm down here and I do this. This is the magic symbol for a global assignment, and you put in X gets 1. So one of the creators of R, Rossi Haka, he's a funny guy. He's funny. He wanted to put in. Sitting in my house when they say, I want a function in R that comes out of the screen with a boxing glove and hits the user. Okay, global variables are just an extraordinarily bad idea. Okay, okay, in any programming language, especially in R. Okay, on next Tuesday or Thursday, I will show you not global variables, but non-local variables, which are better. Okay, so they're not global variables, but you never need global variables. They're just bad news. Let me just go over here for one to do one little thing. So here's a list of what we're going to talk about today. But I in my notes from the last day, I had there's a piece on this thing called attach, which is related to global variables. It's very convenient. Oh, I hate typing mtcars $mpg, mtcars $wt. Okay, it is annoying. Just like I just really want to say, look in mtcars for the weight and the miles per gallon. Okay, so people do this attach business. Okay, and it's the world's most bizarre thing, okay? Because then they make changes to the columns, okay? They go, oh, let's go and change all the missing values to 10, okay? And what you end up with is 3 copies of that vector, and it's always in the wrong place that you did not anticipate it being. And this is where global variables. This is very much global variables, okay? So where will this go? If I put a command in here, where will X go?
All of them, or?
No, God, no. It will only go one place. Okay, but I have no idea. I actually have to know about the context. Basically, what it will try to do, it will search along here and find X, and it will replace X there. Okay, and it's just a very bad idea. Okay, it's because there's no way you can reason about it. And if this is the other thing, again, just to get into the technical details, or but again, if you do this and X lies along here, let's change it to pi. Okay, it'll find it in base and then it'll smack you and says you're not allowed to change anything in a package. Okay, so good news, things will fail badly. Okay, but if somehow you've managed to get X into one of the parent environments, then it will change it there. Okay, it will basically look along the parent environment. Okay, well that's where it will search, and that's so. There is this nice trick, so there is one place where non-local variables, things that aren't local to a function, are very useful. Okay, where you actually hold state across function calls. These are very powerful, and that's when you use this operation. Okay, but not in general. So,
I have another like bad news question.
okay.
So if you actually do use that attach function and then force the parent of a global environment, I know I got to nail the part, but
And I mean never. I put in a caveat, you know, only if it never changes. By the way, sorry, just 1 second. So the idea, just to make it clear what this attach is doing, you attach a data frame, you put it here, and now the variables in the data frame become variables. So the columns in a data frame, we'll talk about that, become variables here. So when you type MPG plus WT, it just searches along the search path and finds these variables in here, and life is great. There's a much better way of doing that, which is saying with MT cars, MPG plus WT. Okay, this is equivalent, but it's much saner. Okay, so this says, okay, start looking here first, and then use the regular search mechanism. Okay, and then so it's the same shortcut.
So for whatever stupid reason, you just assign base as the parent of the global environment using attach. Can you, like, you change in the search path, but can you reverse that? Like, can you actually?
So whenever I put something into the search path, okay, so there's a library function, okay, to load a package. There's no unlibrary, okay. So there's no function to say unlibrary this, okay. But there's an attach command. It doesn't exist. You never heard it, okay. Don't ever type it, okay. But there is a detach, okay, and you can say detach package XML. For example, and that will remove this and splice everything back together again. So you can add to the search path, and you can remove things from the search path, and you can completely control what order is in the search path. Okay, happy? Good. Yes.
So when the promises get evaluated, it's always going to go through the search path, right?
Sorry, we're using the term search path. We have to be careful. This is I typically talk about the search path as being the result of a command search, and so that's only for what's from the global environment onwards. You can think of these as search paths, but they're different from this one over here. That's why I'm drawing a separation. That's why I've put this two different worlds. Okay, but yes, we will always look along the chain of ancestors of environments. Yeah, and that's true for the promise. And the magic trick is that when we got this promise, okay, which was this command MT cars, I said, don't evaluate it now, just get ready to if we ever need it. When R actually saw that in the command, it grabbed this command, but it also said, and I need to know where to evaluate it. So it grabbed the environment along with the command. So a promise is actually an environment and a call. And just for fun, seeing as we're here, okay, it's also a value. Okay, it's actually got three elements that are essential. And that says, and what actually happens with a promise is this value is not set, then we evaluate the call in this environment, we get the result, and before we return it, we store it, so that the next time around, when somebody asks us the value of the promise, we just evaluate it. Sorry, we just give it so we just get the value rather than re-evaluating it again. Because that'd be very bad news if you re-evaluated it every time and you were generating random numbers, or even worse, you were actually doing, 10 hours of computation and you're just repeating it over and over again. So this is what a promise is. And again, no one needs to know about this, but if it helps them understand that, that's exactly what's going on. And the reason, and again, I'm showing you, the purpose of this mini workshop is to actually to tell you things that you won't find in books necessarily, or go a little bit beyond. When do these things arise and all that sort of stuff? I was showing Matt and Clark this thing yesterday. Here's y tilde x, a formula for a linear model or something like that. Amazingly, if you do this in a function, okay, so I'm going to do this, okay, f is a function, x equals generate terabytes of data, Okay. Well, let's actually do it. The Z equals generate terabytes of data. And by the way, return a formula, either directly or in a list or something like that. Okay, as part of what we return, we just return the formula. That has grabbed the call frame, the environment, and it is holding on to all of the data forever until you remove the formula. So it's kind of like a promise in some regards, but it's trapped things, and it's very surprising. You go, wow, why is it using so much memory? Because formulas trap their environment just like functions do, and this is an important thing. We'll talk about that next week. But okay, any other happy?
When do they go away?
Which?
You were saying that when the promises get evaluated, it's like an accordion.
Oh, no, this is the call stack. So when I call scatter.smooth, then it calls XY coords. Now, XY coords needs X, so it has to go and evaluate the promise. That's where we got this extra, this box down here is to evaluate the square bracket empty cars. When that does its job, it returns, and then this guy disappears. Okay, and now XY coords goes on to the next step. And it does something like, it calls another function like plot or something like that, in which case then we get another call frame. So we had one here which was square, we had one which was square bracket. It finishes, the second it finishes, the call frame disappears. Okay? And now we move on to the next instruction. So XY coords is these 4 commands. Okay? So we execute this command, it gets a call frame. And by the way, that calls a function which calls another function which calls another function. This function calls 2 functions. So we get a call frame, then it goes away, then we get another call frame for this. Then that finishes, it returns its value, and then this one goes away, and then we go on and we get more. So these things are, this is a stack. Okay, and they're just constantly sort of being created and go away. Okay, and they last as long as the function is being evaluated.
But the values still are stored.
This is which values? The promise or this is unrelated to the call stack. The promises are just are.
Oh, they're not part of the call.
The promises are not. The promises are merely just a way of actually getting a value, but lazily, only when we need it. But if I do something like this, if instead of empty cars, I just put in the value 1, okay, then it's a literal value. There'll be no need to evaluate that call because it's just a literal value. Whereas in this case, this is a call to the square bracket function. So when I ask for the promise, then that will induce yet another call, okay, and it will then take place in the call stack at the time it's needed. Okay, and again, we'll look at this next week when we start debugging stuff. It looks like it's out of order because of the lazy evaluation. It's like, well, you should have done that when we started, but no, it actually happens later on. So it makes it hard to read the call stack sometimes. Oftentimes, and this is one of the annoying things about it, oftentimes R will say, you got an error in this function. You go, I never called that function at all. And it's like, no, somebody else called that function. Okay, great, but hang on a second. The error isn't in that function. The error is way back at the beginning because I misspelled empty cars, but it actually got down 12 levels and then eventually sort of said, now I need that thing. So it can be very cryptic. Somebody had a hand up. Yes?
When you call debug R Studio specifically, those things are incorporated, like each time it goes into R persona.
Yep.
So that time it's going to go into changes.
It'll show you what's in the call frame. Yeah. Sure. Yeah. So you have access to that. If you use that interface, that's great. But underneath this, it's drawing on R itself. So it's great. You're just seeing it in a different way. But yeah, and it's very convenient. Yeah. Everyone happy?
Just a quick question. So does this, it's more philosophical.
Oh, well, that must be quick then.
So does this knowledge, does this apply more to thinking about how to present bugs or debug things, or do you actually use it to think about how to write code more efficiently?
Both, for one, and secondly, to me, Matt was looking at some of my code a couple of days ago, and he was just saying, and he knows R very well, but I was like, I just don't quite know why that works. I mean, there's an example where I basically, we haven't talked about writing R functions, and we'll talk about that next week. But you know, I tend to write R functions with basically this bizarre circular pattern where the default values of each parameter depend on the default values of other parameters, and you go like, this cannot work. So something has to be evaluated at some point first, and it turns out to be, and that's the sort of thing where it helps to debug, definitely. It helps to write efficient code as to know what's going to actually happen. But it also just helps you look at people's code and it's like, how can I reason about it? You know, that to me is that's one of the reasons I wanted to do this is, you know, we'll talk about a lot of gotchas and things like that today about, you know, this language can be funny and again, how do you reason about it? But it's just like, when you look at this, how can I actually puzzle about what's going to happen? Because it's very hard, and I can give you a bunch of rules, like sort of like, okay, in a package, we look in the namespace and you have imports and exports and all that sort of stuff. But to me, it's like, well, actually it all boils down to one rule, which is the parent environment. Now when you get, so this is when you do get seriously stuck and you go like, I have no idea why it's actually coming up with a value of 2. You know, you can actually go and chain everything together, but ideally that you can actually reason about it ahead of time, both for efficiency purposes, but also just to be able to read people's code. I think about it as like a regular language. If you're struggling, if somebody teaches you Spanish by showing you 10 canonical sentences, you pick up the pattern, but you don't have the grammar, and that's the problem. And that, to me, you know, as I say, this is optional. You guys are all self-selecting to be here, so it's kind of like, okay, if you don't get it, that's fine. It's no real harm done. And so that's about it. Okay. As for this formula business, as I say, this is kind of weird. This is, you know, for efficiency purposes, that the fact that it's grabbing the environment means you actually should really reason about. So we never use Z here, but yet it's got a hold of Z. And it's grabbed that in the environment. So a trick here is either to put the right environment on the formula yourself, or at least to remove Z before you return the formula, and then good things will happen if this is terabytes big. And that's for you know, but you have to understand this. Most people don't need to understand this, and it doesn't show up. And then all of a sudden it's like, that's why R crashes, because I'm doing this 10 billion times and I'm running out of memory. Okay.
It's really just about understanding that chain of events that's occurring because of whatever you typed.
Exactly. Or somebody else typed. Yeah. And to that, and the most obvious case is debugging. And the next obvious case is efficiency, when you need to make it go faster. But then the other one is just like, I like to be able to read code. You know, nobody wants to read code. I tell a lie. But you know, and that is actually that's another thing. The best way to learn R is to actually look at really good R programmers' code and try to figure out what they do. The hard part is to figure out who are the really good R programmers. But you know, it's like any language; you actually have to sort of experience it. Any other questions? When I teach, by the way, this is all I do. I walk in and I go, I have a whole lecture prepared, but we're just going to ask questions, because I'll get to the topics I want, but through questions. So questions are really helpful. Okay, so no other questions. So, okay, so let's say if you get it, great. If you don't, hopefully you picked up the fact that these environments exist. Matching arguments. The one thing you really want to remember from what we talked about is, if you actually want to specify a value for a parameter, if you want to give an argument to a function where the parameter name comes after ... you have to give the full name, okay? Or else you will be scratching your head for days trying to figure out why it's matching the wrong thing. And match.call helps you in this regard. So this is another case of when you get a quizzical result, you know, one of the things I suppose I'm trying to do with philosophically is, if you understand this stuff, you don't need other people to help you. Okay, you can still ask for help, but it's really nice to be autonomous. I hate this idea of people going like, oh, I'm stuck. I have to wait till Monday till I find somebody. You know, now, okay, we have the internet and all that sort of stuff. We have Stack Overflow and so forth, but it's kind of nice. You don't know how fast you're going to get a response. And if this is going to be, I'm not going to get a response for 3 weeks, then you have to be autonomous. Okay, so this is the somewhat easier part, and much more, partially because it's much more common. These are we've talked about the language. Basically, there's only one real thing in the language. Everything is a function call. Okay, it's either a value bound to a symbol, or it's either a literal value, true, false, okay, a string or a number, or it's a value bound to a symbol, or else it's a function call. Everything is a function call. If you get how you match parameters, if you get how the calls work, you're done, okay, on that front. And then there is this thing. It's a data analysis language, okay? This is what we use it for. This is why it's designed the way it is, for better or for worse. So we need data, okay? So you now have data types, okay? There are, and again, hopefully all of this is reasonably familiar to you. Hopefully I'll throw in a couple of things that you may not have thought about, you may have encountered and gotten frustrated with or whatever. And then we'll talk about subsetting. How many ways are there to subset? I got 10, okay? There's basically 5, and then I can never remember the 6th. Oh yeah, and then you get to 10, okay? We'll go through these. And again, this is all incredibly, to me, that there's an elegance to this. It's all relatively straightforward. So what are the basic data types? Okay, we have logical values. We saw trues and falses. Okay, again, I think I have notes up for here. If there's any missing links, please let me know. If there's any errors or things that aren't clear, if you can point me to where things were a little ambiguous, I'd really appreciate that. The common data types are logical vectors, integer vectors, numeric vectors, character vectors. And so let me just be clear here. There is no such thing as a number in R. And there is no such thing as a string in R. Okay, a character string. Okay, they are all vectors of length 1. Okay, in statistics, we rarely have a sample of size 1. Okay. Okay, it's just not worth it. Okay, can't even compute the standard deviation on this. Okay, on a sample size 1. We typically have n observations, and we deal with things on multiple observations all in one go. We take the mean of them, we add 2 to all the values, we turn them from Fahrenheit to Celsius or whatever it is. Okay, and we do them all at the same time because we're treating them all homogeneously, if you will. Okay, we're treating them all the same way. And this is a vectorized language, and it is ridiculously different from C and Java and Python to some extent, and these other languages which are based on scalars, and then building up arrays of scalars. So we actually have, so in many languages I have these basic data types, these primitive data types, which are numbers and strings, okay, and Boolean values, logical values. And then we build up arrays of these, okay, collections of them. In R, we just skip all of that, okay, and it makes it slow, and it also makes it really fast, okay. You get, it's a double-edged sword. Okay, so, but if you try to fight R's vectorization, you lose big time, okay? It will just, lights will dim, okay? Your PhD will take years more longer than it will, okay? It's a highly vectorized language. And what we mean by that is, okay, so, and again, I hope many of you know this. I don't know how it's taught in other places, but basically what we have is an ordered collection of objects, okay, let's just say of values in here. These are ordered. If you think about this, I told you it's a data analysis language. In general, we don't care about the order. It's a random sample. The order doesn't matter. For computational purposes, we do care about the order because oftentimes we'll have 2 vectors, and these guys will correspond to the same observational unit. And I've been told about this. I love this story. 2 different students have run a regression by sorting this, and then running the regression, okay? Breaking all the connections between the observational units. This is a very bad idea. And it's amazing. They always turn out to be positively correlated, okay? So the order does really matter in many cases. We also take subsets of these. So we'll take this guy, and this guy, and this guy. When we do that, we will get back a subvector, okay? Totally independent from the first one. It will be a completely separate set of values, very much conceptually related, but a totally separate copy, okay? And that's one of the other things which I mentioned yesterday, but going back to how functions are called, we pass in empty cars of the first and second columns. We are making a copy of that, okay? R is slightly smarter than that. It doesn't make a copy, but conceptually, any changes that are made in any of these functions to its inputs are not seen by the caller. Okay, and likewise, when we take a subset of this, we're getting a copy of the individual elements. So we talked about so there is a logical, there is an integer vector, there is a numeric vector, and a character vector. Okay, this is a collection of strings. Okay. These are your 4 basic types. They are all ordered, and what is absolutely essential about this is in a logical vector, every element has to be true or false. I cannot mix a number in here. If I do mix a number in here, I'm more than entitled to mix a number in here, but R will not let me maintain it as a logical vector. It will actually, if I combine a logical and an integer value, it'll make them all integer values. Okay, this is implicit automatic coercion. Okay. What's key for each of these is every element has to be the same type. And that's actually a very limiting feature, okay? Because I can't have a date in here and somebody's name, okay? But we have a mechanism for that, okay? Okay, so these are the atomic vectors. Everyone with me? You have a question?
Well, I guess explain a bit and then I'll ask later.
Okay, so these are the basic types. So basically, and there is a way to construct these. There's many ways. You can call a function like rnorm. Okay, rnorm of 10 will give us 10 values from a standard normal. Okay, this will be a vector, and it'll be a numeric vector because they're real valued numbers. If I call r Poisson with 10 and 1, I'll get y. That'll be an integer vector because Poisson random variables are integer valued, so it knows to do this. But you can also do this sort of thing. C of 2, 4, and true. So what's the class of this? Integer? Numeric?
You have to put else before after the digits to make it.
2.3. 2.3, clearly numeric, okay? Because this is numeric, this is something, but it has to be raised to a numeric or else I lose information. If I bring this down to an integer, 2.3 becomes 2, I lose information. So we always have to go up so we don't lose information, okay? And 4 is actually a numeric value. If you take, what's the class of 4? It says I'm numeric because R doesn't treat it as an integer value. We have to put an L there to say it's an integer, okay? And just I like my little I enjoy my little stories. I changed that once. I changed it so that it would actually interpret 4 as an integer, and I didn't get a prompt. R failed to even give me a prompt. Okay, everything breaks. Okay, so everything will have to get changed. So this, if you need this to be an integer, you have to say 4L, or you have to say as.integer of 4, and then that will make it an integer. Okay, either way, it's just syntactics. Yep.
What if you assign x and numeric value, say, of 5? And then
this guy here?
Yes.
So x equals 5.
Yes. And then
I'll say 5.3 just to make sure it's numeric.
Sure. And then in that vector C below, you remove that integer, you put them all numeric, like 2.3, 4. You can put 4, but just remove L.
Okay.
And then you add x at the end of the true. Why does it turn it into character if all of those values have a numeric representation?
Okay, so what's C for? Concatenate, combine. I don't think anyone actually knows at this point. Okay, got lost in history. Okay, okay. So it concatenates them. Okay, this is a bad thing, by the way. This is a gotcha. Okay, later on we'll see. I have written code not not just a few months ago where I got bitten by this, or I go like, what's it? Oh, I see what it's doing. I meant list here, not C. Okay, so it's doing a lot of work here. Okay, but what's going to happen here is it's going to be 2.3. So let's be clear here. And again, please just ask lots of questions. This is what this is actually doing. It says 2.34. Actually, let me just show you this. What is the definition of C? Remember, everything's a function. We can take a look. There we go. Okay, it takes any number of arguments, and then it has this recursive equals false. Again, if we want to specify recursive, we have to specify it fully because it's after the ... If you put in R equals true, it'll put R into the ... and you'll go, hey, where did that come from? But what's going to happen here is this. It takes this, there's a vector of length 1. It takes another vector of length 1, okay? And then it takes another vector of length 1, which is true. And then it takes this thing. It just goes and evaluates X, which is a vector of length 10, okay? This is numeric, this is true, okay? This is illogical. Okay, so this guy has to get upgraded to a numeric. This is numeric. It'll give us back numeric.
I tried that. Well, with the X, we send to some value. And
then, some value. Yeah,
no, some numeric value. And it returns character to class.
Nope.
Without quote, I put X without quote.
Nope. Guarantee it. And this is where it helps to know how to reason. You go, nope, can't happen. Okay, so this is where I say, okay, now you did something else because somehow. And this is where you start debugging and you figure out. But no, the rule is that basically, if I put in here, if I put the values here, 1L here, a true, and I put in the value, and now I put X in here, these two will get combined and they will have to upgrade to an integer. This comes in now as a numeric, so therefore I have to upgrade everything to a numeric, and life is good. There's no characters in here at all yet. But the second I put this thing in here, string A, now everything has to become a character because that's the only way I will not lose a lot of information, okay? Because now I can trap all of these guys. So this is 1.4796 to 16 decimal places. When we convert it into a character, it will basically represent it as that, okay? But we, see? Trust me. If it comes out with a vector, when you only put in numerics, there's a bug in R. And we would have found it by now. Okay? So that's what happens, okay? And this is very important to know, okay? And as I say, so if I put in something like this, here's 1L, okay, here's true. I put in this guy, and then I put in MT cars. What happens? A list.
What is your empty car thing?
Empty cars is a data frame. Everyone knows what's in empty cars. That's my only example. So empty cars is what's called a data frame, which we'll talk about in a moment. But it's actually a two-dimensional object, if you will. It's actually made up of different types of observation of vectors in it. It's actually a list. This is the key thing. A data frame is a list. What's a list? A list is an ordered collection of elements, and well, isn't it like this? No, the only difference between these things and the other vital data type in R is these guys, as I said, every element has to be of the same type, and they automatically get coerced up to being of the same type. This thing, a list, can contain any element in any position. I can have a number in a list followed by a true logical value in a list, followed by a numeric vector in a list. So here's a vector of length 1, here's a vector of length 2, here's a vector of length 4, and I can put a function in here. I can have another list in here. I can put whatever I want in here, okay? A list is for heterogeneous or non-homogeneous objects. So now you have the full set of things you care about. By the way, okay, who has come across, in R alone, a complex number? What were you doing? Time series, wasn't it?
I'm sorry?
You were doing time series, weren't you?
No.
How did you get a complex number?
Well, now I'm questioning what I
Not a hard number. just yeah.
Yeah, just like population models and
generating like group vector grades.
So eigenvalues and stuff?
Yeah,
Okay, so you can get them through in various ways. Complex numbers are these real plus imaginary numbers. If you remember back to, I don't know where you did it. Okay, I did it in high school, but in different countries. So, but very rarely do you come across complex numbers. Complex numbers come in where? Where would they come in here? These are ordered 1, 2, 3, and 4. Okay, and the reason I order them this way is because this one will get upgraded to this one. And if you only have a logical and an integer, you end up with an integer. Okay, if you combine an integer and a numeric, you end up with a numeric. And if you end up with a numeric and a character, you end up with a character vector. Okay, all the elements get coerced up. Where does a complex number fit in here? We need complex numbers. They do arise in R. You rarely need them. That's why I don't talk about them very often. But where would they come in here? Would they come in here, 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 or here? There's a principle. I can't lose information.
Number.
Yeah, because I can represent a complex number as a character vector, as the real part plus the imaginary part. And there are mechanisms to go backwards. There's an as.integer, as.numerical, as.numeric, as.logical, as.character. You can always go back again. Okay, so once things get implicitly coerced up, you can go back down to any of these levels. So this is why complex would come in here, because we can go up to a character representation and go back. Okay, that's
the same thing happens with function. If you have function somewhere in your empty parse and you enter that into that vector,
it would become a character vector. Is that what you're asking?
Or what will it become? Like what that function is going to be represented as?
This is where C will do things that you want to pay attention to when you use C. It's so easy. Oh, it's just one character, and we use it all the time interactively without thinking. Let me just create a little vector. Let's combine these things together. Sometimes you really mean list. So what if I do this? 1 is equal to true, and then I put in this guy here. Here's a vector, okay? So what's this going to do? It's going to give me a vector of, there's 10 things here. It's going to give me a vector of length 12. Okay, but if I want 3 things in here, with this thing having dimension 10, I need to make a list. But this thing says, trust me, I'll make your life easy. I will actually collapse this all for you, and then I have these nice numbers here, and I have one nice value here with a string, and now everything's gone. They've all become strings, and I now have to go and untangle it all. Okay, and I've got to decompose what C did. Okay, what we actually want in this case is list of this guy, and then I'll get one element with this, one element with this, one element with this, and then my function over here, if I put a function in, and they will all remain sane. If you concatenate a function with anything else, C will basically treat it as a list, because it says I cannot represent this without losing information.
So it's not going to give you an error?
No, let's talk. The great thing is you just try it in R and C, and you really can't do too much damage. So we say C of 1, and true, and sum. And what we actually get is a list. Okay, and I know that we get a list because it has double square brackets as it prints it out, and it prints it out vertically rather than horizontally. Okay, vectors are printed horizontally until they need to wrap around and so forth. This is a list, and why can I not represent this? What if I did decide to do this as a character vector? What would I lose? Because I could actually, I can actually say, hey, turn this into a string. Because I can always then parse it back again and not lose any information. Or do I lose any information? Let's do something slightly different. Would I lose any information if I represented this as a string? Just casually saying hint. I lose where it came from. Okay, I can never get back to that environment again. Okay, without some loss. Okay.
What about those assignment operators?
Oh, it'll take care of all of it. We can easily represent this as a string. In fact, it's written in a file as a string, and then when it gets sucked in and parsed and evaluated, it gets turned into something good. Yep. I can try. Thank you. Why am I saying this? It's again, I have a purpose behind this. It may seem slightly idiosyncratic, slightly arcane knowledge. The principle is we cannot lose information. That's the whole point of this hierarchy. And if R says I would lose information, it says I won't do that. I will actually make a list instead of concatenating these things into vectors.
When you said if we can parse it, we can put it back together. Does that mean that it attaches that part to parent?
No, it can't do that. It can't do that. In general, it can't do that. In this case, it could be smart enough to do it, but in general, it can't do it. Okay, we'll talk about this next week, where functions actually have environments which you may not be able to ever get back again. Okay, they may actually have a lot of information. I'm jumping ahead quickly here just because it's related. Okay, I hope all of you know that R has one magical feature that very few languages have, and it's entirely because of data analysis. Again, this language grew up for data analysis, okay? And it has this notion called an NA, a not available, okay? A missing value. Okay, very, very few languages have this because very few languages need it, okay? And it causes a lot of grief, but conceptually in statistics, you just need to be able to represent a missing value. In almost all languages, you actually, like SAS and Stata, you decide what a missing value is in the context of your data. And you don't tell anyone what it is, okay? You keep it a secret, and then you share your data with that person, and you say, minus 99 could be a value, okay? So you just come up with some nominal value that can never, ever occur. And then all of a sudden you find out it does occur. And then you have to go back and recode everything to minus 9999, okay? And you keep going. R has this built-in NA notion, okay? Okay, so we can combine them in here. So we can say C of NA of 1, 2, and 4. Okay, this is a sample with these three values and an observation which we did not get the value for. Okay, this is very useful. Okay, and we don't throw these away because I may actually have this is the weight and this is the height, you know. And when we go to the doctor's office, we actually got your height, but we forgot to take your weight. I now have information, okay? So there's no point in throwing that observation away. This is actually valuable. So my question is, we'll talk about this in a little bit in a moment, but my question relates to this is, what is the class of NA? Logical? Why?
Because it's saying, is something here enough?
No.
Because otherwise you would coerce the other things in.
It has to be allowed to be illogical so that we can have a logical vector with missing values. And if it was a numeric, the logicals would all have to go up. Okay? So by definition, this has to be at the lowest level, okay, of this hierarchy. Nice job. I like that. Okay, so an NA is logical. You combine an NA with any of these other types, it just gets promoted up to these other types and still remains an NA, okay? No problem.
What's the difference between NA and NAN, if not a number?
I did actually write this down yesterday. There's notes that I would love people to read and give me some feedback on, again, what's not clear and what's missing, because I know there's bits that are missing. What is NAN? Okay, first of all, there's two things that are often confused. That is not a missing value. My canonical example, this is Nebraska. Okay, that is the abbreviation for the state of Nebraska. It is not a missing value. I'm not going to say anymore. Okay, this here, when I type NA, that is a missing value. You can, if you want, type in NAN. You wouldn't ever. Okay, NAN stands for not a number. Okay, and what it means is you've done some computation that resulted in not a number. Okay, like taking the log of minus 10. Okay, is what I wrote down yesterday. Okay, you cannot take the log of a negative number. That's your problem. It's not an error. It's just not a number. Because if I do something like, if I take the log of x, I don't know what's in x. That came from some other computation. So it comes back with 1.73. Minus 2, and this one was not a number, okay? And if I pass in x as being this, if I have a vector of this, which is 2, 7, and NA. This will come back with the log of 2, the log of 7, and the log of an NA. What's the log of an NA? Pardon? NA. Okay. Okay. So we'll play this game now. It's always a question of when we get there. Okay. I'm thinking of a number. Add 1 to it. What's the number?
1.
You don't know. I didn't tell you. Nothing you can do to an NA can reveal its identity. Okay. So because if you said, well, I know the answer is 7, and you added 1 to it, well, then I kind of know the answer to the previous question, which is what's the number. Okay. So these operations in R, NAs get propagated. Okay. If you put an NA in, you get an NA out, okay? We saw this yesterday with the sum function, sum of all these numbers, and they had this NA.rm equals true at the end, because if you say, add up all these numbers, and you go, okay, I did, but one of them's unknown, well, then therefore the ultimate answer must be unknown, okay? But you can say, you know, can you just omit, can you just ignore the missing values? Yes, you can. But otherwise, the missing values propagate. And this gets us to this other point, okay? Which is this log function, okay? Here is x, okay? And so whenever I teach my introductory stack computing class, I look at the first assignment and go, great, I know who the CS students are. Because when they want to compute the log, they do a loop over all the elements in X and squirrel the answers back into another array that they allocate, and life is good. Whereas we just go, oh, you mean just log of X. Yeah, that's what I meant, okay? And this is way faster, way faster. This is a vectorized language. We only have vectors, and the functions that you learned in high school as being scalar functions, you give the log a number and it gives you back another number, exponential, sine, cosine, all these things, okay? What these things, these work by giving you back vectors, the same length, okay? This is your input and this is your output. It operates, takes this value and puts the log of the value in here, takes the log of this value, puts the value in here, and so forth. It works element-wise, okay? And that's what we mean by a vectorized language, okay? First of all, we only have vectors, but the vectorization is that these functions operate on elements all identically and then give you back the corresponding value, okay, element-wise. Is that clear? If you fight this language, you will lose, as I say, okay? Just because if you start looping over this thing, you write way more code, and it's really slow, and this is just very, very elegant, okay? So when you're doing these sort of things, so, you know, so what are we doing? We're sort of taking, you take the density of an exponential random variable at the observed values, okay? And then you take the log of each of those guys, and then you take the sum of these guys. This is vectorized in X. It takes X in and gives you back a vector of the same length as X. Then we take the log of that thing and it comes back with another vector the same length as X. And then we take the sum, which just is an aggregate function and operates on the entire vector. Okay, and this gives us the log likelihood all in one line, as opposed to a lot of looping and all that sort of stuff. And this is a vectorized language. Okay, many functions, not all functions in the core packages in R are vectorized, and you really want to use them to do that sort of stuff.
There's a loop under the hood, right?
There better be. It's good. Or else we just give you back random answers. Close enough. It'll be much faster if we just give you an answer.
Why is it that our loop will be more inefficient than the loop that's in there?
Okay, you asked. And okay, what's the question? Why? So there is a loop. Look, this is data analysis, okay? So I'll tell you what happens, okay? Sum, I think we have it just here. This was the sum function. It's a dot primitive. There's two things that you can call it. When you see these things, if you see a dot primitive or a dot internal, you go, okay, that's fine. That's in C code. That's in the heart of R. And if you see a dot call or a dot C, it's in C code, but not at the heart of R. So that's fine. But so these are implemented in C because eventually we have to do arithmetic. You know, we have to actually do basic operations. And the C code is compiled, so it's fast. Okay. I told you yesterday. So this actually just connecting it to what we talked about yesterday. Let's just think about what goes on here. Okay, so we say for I in 1 through length of x, okay? And we put a total here equals this, started at 0, and now we basically say x square bracket I total equals total plus that guy, okay? This is a for loop. How many of you have seen a for loop in R? Bad. Wrong answer. No, it's fine. Okay. Okay, so this is fine. Now, remember what happens? Remember what we talked about? One of the first things we talked about on Tuesday was this. And I said, remember what happens? In C, when we compile that, it doesn't even, the only thing it leaves in the code is the number 3 before nobody sees any code. It's just the number 3 is the answer, okay? When you see something like 1 plus x, okay, it goes and finds x. It knows where it is. It knows where the memory address is. It says, okay, I need to go grab that memory address and take 8 bytes and stick it on this register, and then I need to call the chips instruction for plus, because every chip knows how to add. So it's basically 3 computer operations, okay, 3 chip operations. Let's do this. 1 in R, 1 plus 2. Okay, these 2 we know, okay, they're literal values, plus. Oh, I just erased it. Let's look along the search path. Okay, are you in the global environment? Mr. Plus? No. Next one. And you've already attached 12 million packages, so it keeps going, okay? Okay, no, 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 no. Eventually it finds plus and goes, great, let me match my arguments to your parameters. Okay, there they are. Oh, it's dot, dot, dot. So we go through name, exact name matching. None, okay, fine, but we have to check. Partial name matching, none, because you may have na.rm or whatever it is. Okay, okay, so fine. Okay, now we've, oh, by the way, I had to construct the call frame after finding this thing. Okay, and then we put 1 in here, we put 2 in here, and then we add these 2 things, we put the result back. I check to see if there's any on-exit code. Okay, and then I have to allocate the memory to actually put the answer somewhere. I got to tell R to remember it, and I also tell R that, by the way, when somebody forgets, when nobody's touching this thing, release the memory. Great. So that's fine. So we've done, actually we haven't done anything close to this. Okay, I have to find total. This is just for 1 and 2. Remember, I didn't have to evaluate 1 and 2, but I did have to find plus. I still have to find plus. Now I have to find total. I have to search total. Now I have to find this part. I have to evaluate this part. That means I have to go find the square bracket operator, which is 12 million packages. It's always at base, okay? Then I've got to find x. Then I've got to evaluate I. Where's I? It's up here, okay? Now, so that's a huge amount of computation. We all agree that that's an enormous different from three chip instructions, okay? Okay, that's for the first guy. Second guy, where's total? Where's plus? Where's the square bracket operator? It doesn't remember. So it does the search all over again. Why doesn't it remember? Because this is a wonderful language where people do this sort of stupid thing. Okay, let's change the plus operator equal to some function. At the end of my loop, each iteration in my loop, I change what plus is going to be, okay, and give it some random definition. So therefore, R has to technically look each and every single time to see if it's changed. This is insane. Nobody ever does that, but that's why it's so slow. Okay, because we have to do the lookup. By the way, again, I'm jumping around intentionally. It's kind of fun. If you do this, lapply, sapply, which is also nuts because you just type sum of x, okay, or log of x, and it's super fast. And if x is really, 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 really big, these functions will actually go, in the C code, they will actually go, hey, I got 4 cores. I'm going to actually split the job in 4 and I'm going to go, okay? If it thinks it's going to save time. So, but in R, you just chug along really, really slowly. But if you do sapply of this, okay, or, you know, or if you do something like reduce of my vector with plus, okay, which is still nothing like as fast as these guys, but okay, what's this do? Okay, but let's just stick with the sapply. Here's x and f, which, what does these apply functions? They say loop over every element in the vector and apply this function by calling the function with this element as the first argument. Okay, so it's just a loop. Okay? Notice this. I look up f when I call this function sapply, and never again. So I'm not going back and doing the loop thing. I'm actually finding f every single time. Again, on the search path with 12 million packages, that's expensive, okay? So that's why R is slow, okay? Yes?
Just out of curiosity, you mentioned you have to go through all of your packages to the base package.
Mm-hmm.
Like we talked about in the first day, define,
Yep.
package operators. If you were trying to write really efficient code, just hypothetically, is there a way to indicate to R, skip all these packages because I know where this operator is?
So there's two ways, 3 ways. One is just take everything out of your search path, okay? Have nothing in your search path. Global environment, base, okay? And just detach all of the packages. You can do that. That'll speed things up a little bit, okay? So that's a start. The other thing you can do is this. If you are willing to, I don't recommend it, but if you're willing to, you can say base plus. Okay.
Instead of writing plus.
Yep. So
explicitly telling R.
Yeah, and you.
Plus here.
So and if you say something like, if you say base : sum, okay, that's okay, but you need the ticks for the plus because otherwise it's a keyword. Okay, so the parser will get stuck. So you need the backticks, but that's absolutely fine. Okay, so you can do this, but here's a better way. Okay, so again, jumping around.
Yeah.
Hope that's okay. The good news is, if you want me to jump in a particular way, you just have to suggest. I'm auto-suggestible. There is some. I know where I'm going. There is a method to this madness. Okay. But the other way to do it is to do this. Create a directory called R. Okay, and put your code in here. My code.r. Okay. Then go over and, okay, just put it in here. Then go over and create a file called description, all capitals. Go find one on the internet, okay, and copy it and change the names very slightly. Then go in and create another file called namespace, okay, and just put in namespace, just say export pattern, quote dot star, quote, parenthesis, and you have written an R package. Okay, that is an R package. Okay, namespace, all caps, put in this one line, export pattern, parentheses, quote, dot star, quote, paren. This description, I say, copy it from somewhere else. Go find it. There's one in, there's several of them in R, delivered within R. So there's one for the base package, okay? Just change the name base to be my package, okay? Change the author if you care, okay? You don't have to, okay? That's fine. And then you've written an R package and you can say install.packages, okay, quote of the directory to my package, or you can say R, at the shell command, you can say R command, install my package, the directory in this. You've just created an R directory. So you created a new folder, okay, called my package. Let's call it my package. And underneath that, you create an R directory. You put any code you want. You put a description file under my package. You create a namespace file. And that is how hard it is to write an R package. And that's why many people write R packages. Why am I telling you this? There was something related to your question. Okay. Because if I hadn't erased this little part over here, but I'll do it now. Okay, so you have a function in here. You have a function in here that's called f, okay? Oh, sorry, it's f is equal to a function here, okay? It takes everything. So in your, you've installed your package, you type library of my package. Sorry, is it? Yeah, it did. But, oh, I forgot to plug it in. We're going to take a break in a second. Sorry about that. So you type library my package, and then you call f. Okay, f of 1 and 2. This is your function f over here. Now, if you understood what we were talking about before, and if you don't, no worries, but this is one of the reasons for reasoning about this. F is in this package. When I call f, we create a call frame for f, Its parent environment is the environment of F, which is the package. And what's its parents? What's the parent of this call, of this frame here? This is the call frame for this one called F. This is the my package. This one is any imports. We didn't import anything. We didn't do anything like that. So that this is really, this goes away. And then the next one is base. And now you've eliminated the entire search. This is one of the reasons why packages are actually slightly faster too.
Right. So when working within a package, you bypass every other package because the packages are only importing packages necessary to run the functions within the package.
Is that the dependencies that you might import?
No, I really don't. Okay, so we're getting, so this, I hope, hopefully this is useful. There is, and if we can distill this in any way, I'm more than happy to sort of make this more coherent as you need. There are two ways a package can get access to objects in other packages. One is they can import them, and the other one is they can depend on that package, okay? And when you depend on another package, it goes in the search path immediately. So when I type library of my package that depends on another package, that other package goes straight into the search path. Where? Oh God. We need to control that. So you actually may have to control it. This is where, you know, if I have another package in the search path that actually masks some functions in there, I may end up getting the wrong one. This is why importing is a lot more friendly, okay? Because you're not disturbing the user's search path, okay? And you can, here we're not importing anything. Base gets imported because you can't get anywhere. The actual, I was just doing this with Clark today. I said, hey Clark, let's have fun. Let's change the definition of the word function. Okay, you can't get anywhere after that, okay, but you can. Okay, but basically you need base, so base is automatically imported. But otherwise, what we can put in here is we can say import another package like graphics, so we get the XY coords or something like that. And we can even be more specific and say import from the graphics package just this one function. So, because otherwise we're going to be looking through all of these other functions where, no, I just want this one. But when we depend, we say what we import and what we depend in the description file. But once it goes in as a dependency, that this package depends on another, that other package goes into the search path. Okay?
If you do that, that import a specific function,
yep.
And within that function, you have a course with other functions, then would you import everything? No, and so the beauty of this, and again, I'll say this over and over again. If you don't understand, if this doesn't make full sense to you, no problem. Okay, it just works, and just use R as a good calculator, and just it's happy. But the beautiful thing about this is if you import A from another package, and A calls B and C and D in that other package, it knows where it came from because it has its own environment. That is the package's environment. So it knows how to find this. It's exactly the same search path. Because when we call that function A, we create a call frame, and then its parent frame is the environment of A, which is the namespace it came from. And then everything is nice and clean. So you don't need to call it.
Nope. You just import the ones you want, and R takes care of finding all the bits that it needs. Okay? But good, yeah, it's a very good question, but it flows exactly from the computational model I described with these call frames. Yeah.
Well, in that case, why can't we just put the base, like put the position of the second, like a parent of a global environment, and then we know that most of our operations come from base, and all other functions will still going to be looking for their respective parents regardless. Why? I know it changes the search path, but why is it bad?
Because you can't do nice things like changing the definition of function and while and if. But I like to be able to. You can do that.
As opposed to, let's say, attaching all the packages that stay in between.
There's two answers to this question that I can think of. One is it's always been at the end, and that's primarily because if you don't have namespaces, like in packages, which we used to have, okay, so before namespaces came in, then it would all break. The whole of R wouldn't work. Base had to be at the end because you were only looking along the search path. Okay? So that means if you put base second, and then you put the graphics third, and graphics uses the function plus, it can't find it anywhere afterwards. So it had to be at the end. This goes away now with namespaces, so you could potentially do that. In general, yes, you're quite right. Everything, you could have nothing on the search path. First of all, you just say, you know, you would say my package : that function. You don't need to have it on the search path, and that just minimizes the search path. Okay, you can do that. And because of namespaces, you can always, if you're only working with packages, you don't ever need anything. But the trouble is that we don't do that. Okay, what we actually do, we want convenience. Part of the problem with R is it's two things. It's an interactive programming language, and literally the reason it was developed was, okay, as people sitting in Bell Labs would basically say, I kid you not, back in the early 60s, they used to have programmers for the researchers, okay? And so somebody like John Tukey would sort of say, why don't you fit a model like Y of this thing against that thing and come back to me when you've finished and show me the results. Okay, this would take an hour because it was, you know, ridiculously slow and all that sort of stuff. And then he'd look at it and go, that's an outlier. Okay, go back and take that out and go back and do it again. It's like, and then he'd come back and go, you know what? We need a log of X, not X. Okay, so you're highly iterative, because this is how data analysis is done. It's highly iterative. Okay, we don't know what we're going to do until we get the answer to the current. So this is an interactive programming language. What we're talking about now is writing a package which is not interactive. You're actually writing a piece of software that you're going to call over and over again. It's finished. It's done. You're not going to tweak it. Okay, and that's not the way we work. So so really what you actually need is you need to be able to write functions and put them in the global environment and have them search through and find all the graphics packages and all these other things. And that's why it wouldn't necessarily work. But for production mode, everything should go into packages essentially, and then minimize the search path. But that's another adage is that you do not optimize your code until it's actually doing what you want it to do. Okay, so that's why it originates that way. Let's take a break. Okay, I want a break. Okay, we'll meet back in 10 minutes. So I'm very happy to take questions. This is the way I like things to be, so you kind of drive. But we're hitting a lot of the topics, but again, I hope most of you know that these topics. I'm trying to actually fill in the bits that aren't necessarily obvious from regular textbooks or whatever it is, and some of the background and motivation. Jared asked me, why is it 1L or 4L for an integer? What else would you use? I put this in because it actually makes R a lot smarter. So if you actually while we're at it, so one of the reasons I actually added this feature, people were doing this a lot. They were saying 1 through 8 billion or something like that. They get an integer vector, it's very big, okay? And so they say x equals this. So however they get it, they've got an integer vector, and then people did this all the time. Sorry, they did this, x plus 1. Now, why is that bad? Or why is this much better? And it is much better. Or equivalently, as dot integer of 1. This is very laborious. This is no one in their right mind would actually write x plus as dot integer of 1. Okay, so everyone wrote this because this didn't exist. What's the difference between this and this? Again, you see, I didn't know you asked me a question, so I managed to see. I do always manage to get it back, my questions back to what I want to teach. So what's the difference between x plus 1 and x plus 1l or x plus as dot integer.
Can you answer to the question?
No, you can't answer with a question. That's not an answer.
The first one, it's going to have to coerce that entire vector to numeric before that.
This one has got to become a numeric, and the result will be a numeric, and yet, so not only will I actually make a copy of this, because remember, this is plus x comma 1. So it's a function call to plus. These get passed down by value. We don't change x, so x doesn't get copied. It actually doesn't get copied, but it does get copied to a numeric vector because these two have to be the same type. Okay? And then it leaves the result as a numeric vector, which is not what I wanted. I mean, if I actually care that I'm actually looping over integers, or again, if I use this to subset, R will take a numeric value and just make it an integer, so it knows which element to get. But this is very bad news. So if I have a terabyte of data here, I now have 2 terabytes of data, which is very bad news. Whereas this says, okay, these are the same type. Okay, and therefore the result is an integer, which means I can do this all. I just now allocate the answer. Okay, and R is smart enough that if you do something like this, R can be smart enough in certain cases to recognize that we're going to overwrite the same thing, so it can give up the space here and not actually induce 2 copies.
Why isn't R assumed that one is an integer?
I told you, because when I changed it to make it an integer, I didn't get a prompt back when I started R. The whole world fell apart. Okay, it could easily, but historically it doesn't. And now one of the real problems with a language like R is that it actually has a large user base, and we cannot change it without breaking a lot of code. So when people actually depend on something, we are very, very cautious. There was a subtle bug in the random number generator. Well, we have lots of random number generators, so we added a new one, which is fixed, but we had to leave the old one so that you could actually still do it. So you break things. When I actually changed 1 to be an integer rather than a thing, was actually in the S plus code, not the R code, but actually S, the S language back in Bell Labs, and that hits Fortran code really quickly, and Fortran does not like the difference between those guys, between an integer and a numeric, and we would have had to change the entire world. So just to be clear, this is an object of class numeric that has an integer value, but not an integer type, if that makes sense. So, a number can be an integer, but yet it is actually a real valued number, because real valued numbers are a superset of those things. But it's kind of annoying. Yes, exactly.
All right, I hope my question will be well asked. Why was there a need to have, because in numerical you do have the integers, you know what I mean? Like, so the number 3 is in your numerical, so why was there a need to separate numerical from integers?
Hey, we could have done everything with characters and just represent everything as strings, but we don't do that because it's fast. There's 2 reasons first. When you actually write code on a computer, an integer is represented as 4 bytes. It has a maximum value of whatever it is, okay, 2 to the 32, okay, minus 1, okay, plus and minus, okay. We use 4 bytes. It cannot do infinite arithmetic. Okay, this is a problem. So we can play this game in a moment. So it takes up less space than a real valued number, which actually has to take up 8 bytes. We can have more if we want. Okay, but the other reason is your chip is extremely smart at doing integer arithmetic. It does it differently than floating point arithmetic. And integer arithmetic is super fast. Floating point arithmetic is super slow. I mean, it's super fast in comparison with how fast I can do things, okay? But it is relatively slow, so there's a real benefit from customizing the actual computations to, if we know we're doing integer stuff, we will use integer computations. If we know we're doing floating point, we'll give it up and actually do floating point. So we gain speed on the chip in the instruction set, and we also gain memory efficiency, and that's why we do it. In C, in languages, well, in low-level languages, we actually have things like unsigned integers. We actually have bits, like logical values, which are just represented as a single bit on or off. One of the beauties of R, and one of the entirely constraining things of R is, if you go, we were just talking about computer science textbooks. One of the first textbooks you'll see in computer science is data structures and algorithms. So you learn all about linked lists and red-black trees and balanced trees and all sorts of stuff. Yeah. You got logicals, you got integers, you got numerics, you got characters. Now go away. Leave us alone. Okay, that's it. That's all you got. So it's an extremely constraining language in terms of the data structures you have. We actually have a few others that we give you through the back doors. Okay, but in fact, actually, I counted them up today. There are 17 data types that you will see. There's basically 17 data types that you will see in R, and yet you actually only see about 8. Okay, that's how limited this language is, and that makes it much simpler to reason about, because there isn't this distinction between there isn't a distinction between a single valued number and a vector. Everything's a vector, so you just don't have to worry about it. Everything's got a length, and they're self-describing and all that sort of stuff. So it's much easier to reason about, and for that you get certain benefits, and that, namely that they're customized to integer values and they're customized to floating points. Okay.
I have one quick clarification. So I understand that 1 is numeric. Why is x equals 1 to whatever? You said that was integer?
That is integer.
I don't understand why, because it includes ones.
So technically, and I've actually been having to deal with this in the last couple of weeks so one of the things that we're working on is trying to make R fast, taking your stupid code, your really bad R code, and making it go super fast. It's faster than C code can go. And we're doing that. But so I've had to deal with this. But when you type 1:10, okay, this is numeric and this is numeric. So you would think this is a sequence of numeric values. And if you type in 1.5 up to 10, what does that give you? This thing here is actually, remember, this is a function call. So this is actually 1 to 10. And now you got to look and see what that guy does. Okay, and what it actually does is it creates integer vectors. Okay, by default. Okay, it is actually a shortcut to the sequence function SEQ, and that can do anything it wants. That can take 1.5 and I want to go up to 10.7 and I want to do it in increments of 0.023. It can produce a numeric sequence, but this colon operator creates integer sequences. Okay, when it can. If you give it something too big for an integer sequence, it goes, can't do that. I have to make it numeric. So this goes back to this other issue. The integers have finite precision. Okay. In fact, do real value do numeric vectors have infinite precision?
Not infinite, probably, and whatever size there.
I told you we go into 8 bytes. You can't get an infinite number of things into 8 bytes. We do pretty well. The IEEE 754 standard that somebody came up with is darn smart about how to represent. It's called floating point because we actually change how we represent numbers in clever ways. But you can't actually represent all numbers accurately. In fact, this is one, and this is, by the way, this has got nothing to do with R, but it's incredibly important in all languages, including R. Do never ask, is this thing equal to this thing? Because they ain't. They're never equal. They're just darn close. Okay, and if you actually go in and look, so first of all, so if you actually go into R, there's a dot machine. There's a thing called dot machine, and this tells you all about the characters. This is the biggest integer you can get. Anything beyond that cannot be represented as an integer. It will have to become a numeric value, and R will magically do this for you. If you did this in C, you just get the wrong answer. Okay, but R will, that's one of the reasons. Another reason why R is slow. But there's all sorts of different things in here, and you can find out. But then basically, there's this double epsilon. That is as small a difference as you can detect between two numbers. Okay, so never ask, are these two numbers identically equal? If they're integers, sure, go ahead. If they have certain characteristics that they can be directly represented as real valued numbers on a computer, maybe you've got a fighting chance. But so there's a function in R called identical that says, are these two objects identical? Do they have exactly the same contents? Do they have the same characteristics? Okay, yes. or no. But for comparing two sets of real valued numbers, you want a function called all.equal, okay, which builds in this fuzziness that says close enough to government standards, okay? And that's what's going on. But that's two things. You got machine precision, and you've also got this thing that so if we do something like the following, which is, where is it? Well, so what happens here? So let's take a look at this guy. So oh dear grief, what is going on with my computer? Hang on a second. I have to be in Emacs. So this is the other thing I wanted to touch on. Okay, hopefully you all know about this, but if you don't, this is your lifeline to the world. Okay, and I have been working with this language for an awful long time, and I kind of know what I'm doing most of the time. Okay, and every time I issue a command that isn't completely trivial, I check the answer, because I do not trust that I've got the right answer, that I've done the computation correctly. So I always ask, okay, what is the class of this thing? And this thing is already a numeric. Okay, so I have a different thing. Okay, it's an integer. Okay, so now what's the following? Let me add one value to it. Okay. Okay, and now it's gone into this NA mode. Okay, because it's trying to actually, it cannot represent this properly, and in other computations, R will just do the right thing here and get it right and coerce things into different places. Okay, but so it says it's trying to be an integer, and I cannot represent it, so I get a missing value. Okay, in other cases, it does the right thing, but one has to be careful about overflowing in different ways. Any other questions or follow-up questions on that? Nope. Excellent. Okay. So is everyone familiar with the concept of class? That you just use class to look at this? In our studio, it just shows you the class in the top right. That's fine. It's very helpful to actually know how to do these things on the command line, because you're sometimes debugging where it's not showing you everything. Other times you're actually logged into a remote server which has a lot more RAM, a lot more CPUs, and you don't have RStudio necessarily running, although you should get your code running first on another machine. So what's the difference then? Well, how many of you know about the function type of, T-Y-P-E-L-F? Not everyone. So this is the other thing, okay? So let's just do the following. Oh, you go away, please. Thank you very much. So let's just do the following. Let me just do the following. So LM of miles per gallon for weight of MT cars. This is a linear model. Okay, just fitting a linear model. What is the class of F? Function?
Well, it has to be. It depends on what's in empty cars, because
this is a data frame. This is a linear model. Says fit a linear model. By the way, there's terseness to writing that grew up when people were on really slow connections, with 300 baud modems, where every character was a painful operation. So people became very cryptic about what they actually typed. So this is linear model. So what's F?
Oh, wow.
Okay, it's an object that represents the fitted linear model. Okay, it's an object of class LM. It's not logical, it's not integer, it's not numeric, it's not complex, it's not character, it's not list. So how on earth did we build it? So this is where we want this guy. So class tells me how to think about it. Type of tells me how it was built and on actually how to reason about manipulating it for the most part. Okay, so it is made up. It's a list. What's in the list? Okay, and this is the other thing. So what do? Class of this thing tells me how to think about it. I'm still confused. I've never seen this thing before. Tell me the type of this thing so I have a little bit of an idea. Okay. We can also always ask, what are the names of this thing? That's fine. We have all of these different things. And this is one thing I just want to make I assume people know about it, so I don't want to bore people, but I think it's probably helpful to talk about. Okay, so it has all these named elements in this. It's a list. Remember, a list is an ordered collection of elements, but the elements can be of any type. They don't have to match each other. Vectors, on the other hand, over here, always have to have exactly the same data types in each cell or in each element. We have these guys here, but this LM, it says, it's a fitted linear model. If I look at this, I say, oh, it's a linear model. If I look at a list with these things in here, I don't know it's a linear model. It could be a generalized linear model. It could be a classification tree. It could be just something I found on the web, okay, that somebody just put together for gratuitous reasons. Okay, this is actually telling me how to reason about what it is and a little bit about its provenance, okay, where it came from. This tells me how it is constructed in terms of the primitive data structures that we actually have. So class of is really important. Type of is really important when we actually get stuck. Okay, str of this guy, Danielle's friend, is for structure, and it actually shows you the structure of the entire object. So you actually sort of see there's a model component here. We have these terms. So these correspond to all the names. We saw the names, and we see these elements. It's showing us the names of the elements, and then it's showing us essentially what's in each of these. Each of them is actually, this is a 32 element numeric vector, and it's named, and the names are actually these things. These are the names of types of cars, okay, car models, okay, and so forth. So this str for structure is showing us the entire structure of an object, which is probably overkill in many cases, and it's just, you just look at it and sort of, okay, now I get the structure. I prefer to query my way through and actually say, what are the names? Okay, now let me look at each of these little guys. Okay, and we can actually also, you know, look at this guy, let's loop over this guy and actually ask what the class is of each of these things. Remember what I was saying about sapply? So if you're not familiar with sapply, it is a loop over every element of this thing, and it applies this function to each element, and it returns a vector or a list with the answers for the calling class on each element of this. Okay, is that clear? I can draw that if you care. Okay, so now we can actually go in and we can see, oh, now we've got things. Class has always come back to us as being a single string, a character vector with length 1, which is LM or numeric or integer. Here we're actually seeing one's a data frame, one's a call, one's a list, integer, one's a QR. What the heck's a QR? Okay, anyone know what a QR is? Okay, it's the QR decomposition of the model matrix. So X transpose X inverse, it's the QR decomposition of that guy. Okay, so it's a matrix. Well, why don't you just tell us it's a matrix? Because it's more than a matrix, it's a special type of matrix. That's the definition of a class. It kind of tells us how to think about it, whereas what we actually see is if we go in and actually look at it, it's actually a matrix underneath. But it may be quite intelligent. It may actually only be half the matrix because it's actually a symmetric matrix, so we only have to store half of it. So we've got all these things. But this guy over here, the terms, is actually two things. It's both a terms and a formula. So it can actually have sort of a bipolar personality to actually sort of figure out, and so it can actually represent two different things. But we're able to go and look through these things. And what we've got here is we've got an attribute, which is a class. Okay, we've also got these things which are attributes on the individual elements. We saw names, and these are attributes on an object. Okay, every object has some data, and then we can tag on attributes. The one attribute that you won't see here, but it is on every single object, is its length, and the other one is its type, the type of. Okay, and then we tag on the classes for the non-trivial ones like logical integers. And you can put any attribute you want on it yourself, okay? But one of the key ideas is that when we actually have these things, why did I bring these pens over here? When you actually have these objects, you can adorn them with any attributes you want. You can put anything you want on an object. But importantly, what we have is this. Here's your vector. Okay, and there's your vector, and so we hang off a class optionally. We hang off names. This is very common. We have names, and then I say any other thing we want. And we do this with attributes. We say attributes of this guy, of x. If this is x, we get the whole set of attributes, and we can assign an attribute. Attribute of x, Bob, equals some value over here. We can just tag on anything we want, and then we can pick it up later on. So we can, basically we can sort of have multiple things. While it's still an integer vector, it actually has extra information on it, okay, which is kind of very, very handy. We're going to build on that very quickly, okay? But the names are really, really, really useful, okay? So this is a vector, so I'm hoping you all understand. I'm worried about doing this because I'm going to bore you all to death, but then I find out, no, maybe I should tell you. Okay, these are the ways you subset this guy. Okay, so I've introduced lists, and I told you what lists are. Let's go back to vectors, and we'll just deal with vectors for the time being. This is the subsetting rules. How do you subset a vector like this? Okay. The obvious way is, so this is the value, okay, so this is A, B, C, D, okay? Let's say it's a character vector, doesn't matter what it is, okay? Because they're all the same, okay? Clearly they're integers or numerics or logicals, but the way we think about them is exactly the same thing. The most obvious way that you subset this is you say X, square bracket, and we've alluded to it the whole time, and you basically say, I would like position number 1 and 10, please. Okay, and that will get this guy and give you back a new vector with A and whatever it is, okay, whatever the 10th character is, okay, let's call it H. Okay, so and it creates a copy of these values and puts them in here, and life is good. Everyone happy? If I put down 10 and 2, I will not get this answer back. I will get back H and A. Okay, order matters. These things are highly ordered. Okay, and that's a really important thing. You may not care about the order, but you may, so therefore life is good. How would I get back everything except A and H? Okay, so I can go in and say, okay, well, so what I actually want is number 10 and 2. What is it? So why did I put A in here? It's B. Okay, so I could go in and say I want 1, I want 3, I want 4, I want 9, I want 11, and so forth. And I could.
Those 1, 3, 4 are the literal values or indices?
Which ones? These ones?
Yeah.
These are indices. These are the actual positions, or the indices or positions I want. They can be numeric values or integer values. I don't care. R knows what we're doing here, and it knows if you give me an index of 1.97321, it will round that to an integer. Okay. Go see. Okay, it'll sort. Okay, so it'll go. You put these in. This is too laborious to actually type out, so it's clear. And again, R is a language of convenience for the most part. So what we would actually write is the following: minus C of 10 and 2. Okay, so that just says the opposite. Some people try to do this. It doesn't make a lot of sense. So some people tried to do the following, which is they tried to say, I would like C of minus 10, minus 2, and I'd like the third one as well. Okay, so I want everything but 10 and 2 and 3. I would like 3. Well, that's kind of in the everything else, actually. So you don't know what you mean. Okay, so this is not allowed. Okay, so you cannot mix negatives and positives. You either they're all positive or they're all negative. Okay. Okay, everyone happy? What's that do?
Indexes start with 1, right?
Oh yeah, God yeah. Whoever started counting at 0. The whole world counts from 0 in other languages, but everyone else counts from 1. What will this give us? Okay, well, what will this give us? Okay, so there is a thing, X is equal to letters. We'll do this, we can do this on the computer, you can do it now. Letters is built into R, it's the alphabetic letters, A, B, C, lowercase. If you want the uppercase ones, make it uppercase. Okay, so there's 26 letters here. So what is X0? And what is X of 27?
Will X of 27 be an 8?
You're full of questions. Yeah, X of 27 will be an NA. In most other languages, it'll be smack. You know, we don't have a 27th one. So you're not allowed to go get it. Okay? Is that true? Let's just check. you want to, because, so let's just get letters of 27. That's an NA. So what is letters of 0? Character 0? Okay, so this is actually a really important point in what you just yelled out. This is not always true, but we would like it to be true, and it is true, except for in other people's code. Okay, and one other case, for convenience. When I subset with a single square bracket, in general, again, with caveats, but the default is to get back an object of the same type and class as this thing. So that's why this is a character vector, therefore we got back a character vector, but there was nothing in it. But it's still a character vector. So that's the general rule of thumb. Square bracket, single square bracket gives you back an element, an object of the same class as the one that is being subsetted. And that kind of helps us to actually reason about it, and it doesn't just spontaneously go into weird things. Now, sometimes it does, okay? But in general. So, but what if I do this? Remember, this is a vectorized language, so I should be able to subset multiple things. We do multiple operations in one go. Okay, we rarely go in and just get one observation at a time and then go back and get another one. We just do them all in goes. So what will that give me back?
A and 0.
A and 0?
Oh, character 1 and 0.
Character, it'll give me back a character vector by the rule I just said. Square bracket will give me back an object of the same class as the one that's being subsetted.
I think that's it. So that satisfies the condition of returning the
So it'll give me back a character vector. What's in it? Just A. So we can subset by 0, and that's essentially a no op. Okay, it's just not. It's not. It doesn't do anything. It ignores zeros. Okay, so if we have negative values, it drops them and gives us the result, the remainder. Okay, the remaining vector, the remaining elements of the vector. If we have positive values, it gives us just those, and if we have zeros mixed into positive values, it just silently ignores the 0 and keeps moving. Why would anyone? Then why would you do this?
It's just the way you set up the index.
Well, no, why would I care about this? I mean, why would we put this into a language that says, well, who's going to? I don't want that one, so I'll explicitly type out 0. It's like, are you nuts? Why don't you type out 10 zeros for all the ones you don't want? Okay, you can go. There's a reason why we want this. Because most of the time, we're not actually typing out the ones we want. We're doing computations to find the ones we want. Okay, and so many of you will, hopefully, you will all have done this. I'm going to show you a different way in a second, but I'm just trying to connect the dots here. A lot of times what you'll do is you'll do this. You'll say match this collection of items here into some big long table over here. Okay? Okay, and you're basically saying, for this element here, find out which position in this table does it correspond to. So this is A, and this is an A over here, and this is X, and this is Y. Okay, so A goes to here, and this is position number 10. So this match comes back with number 10 in this position. Then we move on to this guy, and this is D, and D goes over to here, and it's a position 99. So we find these matches. And then for this one here, it's XYZ, which doesn't exist at all. So we come back actually with a missing value. We don't know where it is over here. It's not 0. It's not -1. I don't know where it is. It's not in there. So it's missing. Okay. So now what happens? So now I go off and I have a parallel vector to this. Okay, let's call it P. So I say I is equal to this, and I say P square bracket I. What happens? This is very, very common, by the way. This is kind of doing a simple join across two tables. Okay, we're connecting two parallel vectors. So I basically said, go find me where these elements are in over here, and then I'll get the corresponding elements out of here. So I have 10, 99, and NA, so that's what's in I. So I pull out the 10th element, the 99th element of this, of P, and the, which one would that be? I don't know. So do I ignore it? Should R just say, I don't know what it is. Here, I'll just give you back the 2. Or R is going to just say, which one would you like? You're not telling me which one you want. So I'm not going to give it back to you. I'm going to say, I don't know which one you want, okay? The index is unknown, therefore the value is unknown. So we will get back 10, we will get back whatever it is here, the 10th element, the 99th element, and an NA. But I don't want that. I actually want to get back nothing. Suppose I want to get back nothing. We can deal with that. We can deal with the NAs, but it's easier at times to say, no, I don't do. So match actually has an extra argument, X, Y, and what to do if there's no match is, by default, it's a missing value, NA, but we can put in 0. And now we would get back 10, 99, 0, and the match would do, and this subsetting would just be perfect. It would come back with, and ignore the things we actually want, okay? So the 0 is actually kind of a handy thing, okay? And it's especially handy in this case of match. Nobody wants to type 0. That's completely pointless to type 0, but if you can generate it as the result of a computation that you're going to feed into the subsetting, then it's a good thing. Yep.
So getting back to the original question, the reason why you index by 1, starting at 1 in R, is to utilize the 0 as a sort of placeholder.
No. The reason is the reason is because humans think in terms of 1, 2, 3. You know, if you ask a child, you know, go pull out the first element there, they will not say, oh, you mean the 0th element? The only reason people count from 0 is because of C and Fortran and languages like that, and that is, and Fortran doesn't even. Is because it's a trick, because if I have 3 elements and I have the address of the first one, how far do I have to go to get the first element? 0. That's the only reason. Okay, so it's distance, okay? Whereas we actually count at 1. It's the first element, second element, that's all. So it's not because of 0 that we want to use it.
In the context of the subsetting rule, you can use 0.
Now we're
return or
just to,
values that don't match.
Yeah, exactly. Yeah, so exactly. So it is a helpful little thing. It's a nice little trick to know. And again, just part of it is just for completeness as to what's actually happening. Okay, so you can index by position. You can use subset. You can subset with 0 inside the positions. You can index by negative numbers to omit those values. And then we can also use names. And these names are incredibly important. Okay, what we actually do is we put names. We often put names on the elements here. And if you put a name on any element, every name has an element. It may be empty, but every name gets an element, okay? They don't have to be unique names, okay? You can call 2 things Bob, okay? Doesn't matter. It's up to you how you use them. But if you do put names on them, and you call this X, and this is, okay, so this is now, I'm going to change this example to be X is 1, 7, and 9, and this is A, B, and C, okay? Then basically what can I do? I can basically say X, and I want give me A and give me C, okay? And now I'm subsetting by name, and this is really handy because you know what? We don't think in terms of positions. We think in terms of identity, okay? So we actually want that element. We want the element named A, and we want an element named B. And oftentimes we actually have multiple vectors, and we have the same names because they correspond to the same observational units. So now we can actually easily subset between them. Because now what I can do is something like this. Okay, well, we can do it in various different ways. But I can always say names of something, names of X. I can say class, type of, length, and names. Those are the ways we query, the default query mechanism, and then the str function. But names of X tells me what I have, and then I can use it to subset, and I can then use it to actually go in and find these elements in part of a bigger thing. So if by chance I had something like the following, I basically say, okay, give me back all the X's. And now we're going to, okay, so if I know where they are, so this is the other piece of obvious magic, I hope. Okay, this is what we live off of. Okay, I want to go and get all the values in X which are bigger than the mean. Okay, so first of all, I compute the mean of X. Okay, if there's missing values in there, I better put na.rm equals true. Okay, but now what I basically want to say is, well, what X is greater than the mean of X? Remember, this is a vector, so we're gonna get lots of topics in here in this one little example. Okay, this guy here is a vector of values, whatever length. This operator here is what you think it is, but it's a vectorized operation. Remember, everything is vectorized. So what this is going to actually do is compare this element with that element and put a true or a false in. True, okay? This element with that element, which is false. This element and so forth. And we get trues and falses coming back here, okay? And that's great. And I can now say sum of this to find out the number of trues, or I could say table of this to find the number, the counts for each category, true or falses. But what I really care about is, let's just call this W, because I actually now want, I don't want to know if it's bigger than X or the mean of X or not. I actually want all the X's which are bigger than the mean. And now we're just subsetting by W, okay, which is the logical subset, okay? Vectorized operation, very, 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 very important. Everyone, this is completely obvious?
Not quite. So if we ask for X of W, it returns the vector of values that are larger than mean, right?
What we're actually getting is here is this. We get a true, false, true, 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 false. So I like to draw it this way now. I like to draw it this way for doing the operation. Then we draw it this way, okay? And now what basically, so this is W, okay? So we've got true here, and we've got false here, true. Okay, let's do this. Let's just color them in where they're true, okay? And now I've got X, which has to be exactly the same length. Didn't I just say that? It's vectorized so it has to give me back the same length as this. So this is X, and I got these values. So what I do is I pick this up and I put it down. Okay, and whatever is covered, I take. Okay, that means I don't take this one and I don't take this one, but I do take this one and I do take this one and I take this one. Okay, so it's a mask, if you will. It's okay. We just put it on, and whatever's covered is the bit that and you think about them as magnets. They just go in and pick everything up, and I end up with a subset of this, which is just 3 long. Okay, happy? So this is incredible. What I see a lot of people doing is this. They do this, and they've been taught to do this. This is W equals this guy. And then they go, okay, they don't think X square bracket W. They go, okay, tell me who's done this. Who's done this? Oh, come on, who's done this? Okay, so this which guy says, go through a logical vector and tell me the indices or the element numbers which are true. So it goes through this guy here and says 1, 3, and 5. And now we go back to our rule over here, which is we're subsetting by position. Okay, so what happens when none of them are true? What does which give you?
NA.
NA? No, can't give us
The character 0.
the character 0.
Well, when we asked before which was letter 0 and it came back an empty character vector.
So it wouldn't give us an empty character vector, it would give us back an empty integer vector, okay, because which gives you back integers because it's telling you the positions. So then what happens when you subset by an integer, by an empty integer? Do you? So yeah, not in the same class, always the case sort of idea. But so, you know, if we just basically go in and say, okay, subset by this guy, okay, so we do get back kind of nothing. So it kind of behaves itself. This is an extra computation that you just don't need, okay, and it can actually cause you some grief. Okay, there are times when it actually, the degenerate cases where you just don't need it, whereas just subsetting by the logical value is faster, more straightforward, and less error prone. Okay, but sometimes you actually really do need to know the positions. Okay, but that's fine. Okay, so as I say, I'm going to jump around. There's lots of ideas. So please, you have to ask me questions if you're not. If you want to follow up on something, I could. And let me just ask. Let me ask you this. So logical subsetting is phenomenal. If you just stick a not W inside in here, put this exclamation mark before a logical value, that's the unary operator. It just takes one argument and it converts all the trues to falses and all the falses to trues. So it's a very easy way of masking it out. If I do this, let's do 2 things, okay? If I do this, and I pull out this number, I pull out this guy and this guy and this guy. This guy will actually retain names of A, C, and D, E, okay? Okay? Now, if I have another vector over here, huge, much bigger than this one, but this has the names, the same names, I can subset by the names on this. Go find me essentially the names of all of the x's which are bigger than the mean, and let's get the names of those and use them to subset into here. Okay, so we really do actually use a lot of different types of subsetting, by position, by logical value, by names. Okay, so we can just type the names in as we want, but we typically do computations to get those names. Yep.
Can we use that operator in the red, the line that we call x minus c 10 and 2? Like we don't want a 10-second position. Can we use instead of minus? Can we put that exclamation mark?
No.
Say no.
No, you can't. So you can't put an exclamation mark in front of an integer vector, because the exclamation mark doesn't understand what that means. Okay. So I mean, I don't actually know what it would mean. I mean, what you can do is, if you really wanted to, but here we're subsetting by position with our negative position. Over here we're dealing with logical values. Remember, and again, this is why the language is so simple. Okay, if you wanted this to work where w was an integer vector, this guy here would have to look inside what it's trying to index on, and instead of doing this computation, it would actually have to go and do something else. So this would break. Square bracket would actually have to know how its input was getting calculated to do that, which is a very bad idea. Okay, so and this guy here only needs to, this exclamation mark only needs to know about one thing, which is how do I turn trues into falses and falses into trues. So each function has one task and one task only. That's a really good principle. Okay, and we don't need this. So I thought you were going to ask, because I got this question right a lot. Can I do this? Minus c of a and b. And I've just answered that question, so what's the answer?
No. Because I've tried forever.
Well, that's not the reason. It's not because...
It's looking for a logical.
No, it's actually looking for an integer value here, because it's going to be a negative. But the point of this is, where will this fail? So this goes back to the reasoning. This will not fail. This is a good example of, the debugger will tell you that it fails inside square bracket. It didn't. It failed before that, and but it actually failed after because of the lazy evaluation. If you take a look at this call stack, it is actually failing on this command here. Okay. This is a unary minus, so you normally think of two things, x minus y. This is just take -2 or -3 or whatever it is, minus this value. So it goes off and evaluates this. This is simple. It calls the C function and gets a character vector back. And then it says minus a? What the heck does minus a mean? Does anyone know? No one has a clue.
Why wouldn't we use the value that's assigned to a? Like if a is a
No, this is a literal value. No. Remember, once it's in quotes, it's a literal. There's no, that's the difference, what we talked about on Tuesday, the difference between a name, which is a symbol, and the difference between a literal string.
And if we remove the quotes, will it give us the -1 and -7?
No, because these have to be variable names. Because now we're looking on the search path for A and B. We're not going in and looking in every vector going, hey, do you have an element named A? And
We'll put X over there. We'll put X over there.
No, because it has to evaluate this first. This gets evaluated and then passed to this operator. This is why it helps to reason that. And again, everything has to be separate. This computation has to be done separately from the square bracket operator, or else the language becomes so context specific, it's just not worth even having at all. Okay, so everything has to be decomposable down to its smallest unit. And so minus says, I do not understand what to do with a character vector. That's a stupid thing to ask me to do, so I'm going to stop. And again, if you take a look at the debugging in the debugger and the call stack, it will actually be after the call to square bracket, but only because of the lazy evaluation. You got it.
So when it gets to the minus is a function called like plus.
Yeah.
And so then it's going to take arguments as character A and character B.
One character vector. It's going to take. So this thing here is actually going to turn out into a call of minus with one argument, which is C of A and B. Okay, and then so now minus doesn't do much except for it immediately goes and gets the value of its argument. So now it evaluates this expression, which is a call to C, which combines these two literal values into a character vector of length 2, and then it hands that back to the minus function, and minus function now goes nuts. Okay, happy?
Yeah.
Okay, good.
So that's the case for the which.
No, you just, we're going to do it by name. We're just going to actually do this. It's much easier. Okay. Okay. So now we do it by name. If you're going to do it by name, what do I do with which? Which requires a logical vector. Which names are in this? Actually, no, which names aren't in this? That's what I want. Yeah, okay, so fine. So what we would actually do is this, and this is for fun. Okay. So we would actually do something like this: C of A and B. Okay, I'm just going to call this I from now on. Okay, this is my index. Okay, this is you wanted minus I. That's not that. You just literally just type this first. It doesn't make any sense. You get an error, so that's not going to work. But what we can do is we can say, okay, give me all the names of X that are in I, okay? Just gives me back a vector, the same length as the names of X. The names of X should be the same length as X, unless it doesn't have any, in which case it's null, which we've never talked about at all, okay? Which is another data type, and it's a very special data type. There's only one null, and what's its length? 0. Okay, it's its length 0. What's its class? No. Okay, it's very boring. Okay, but anyway, names can be null, in which case then we've got to be careful about that. But if this comes back as this will come back as true, false, false. Oh, it's not true here because we have A and B, and false, 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 false. Okay, and now let's put a not in front of that. And now we're back into the land where we are happy and life is good. Will this give me the right answer?
Where is the question that you're asking?
That's the problem. It may do, depending on the question I'm asking. If all the names of X are unique, this will give me back the right answer. Okay. So what am I talking about here? If there's multiplicities in here, or names of X, yes, I will actually. This will actually still work fine. Okay. And that's fine. But it's different from this, if you will. Okay, we're obviously trying to do something slightly different, but okay, well, we're actually sort of getting trues and falses back. But here, what R will do is it will actually go and find the first element named A and stop. Then move on to B and find the first element. So if there's 2 A's, it will not give me back 2 values for A. It will just give me back the first one. This guy here, because if I basically say, is the names, let's just go to 1, names of X equals A, that'll give me true or falses. So if there's 2 A's, I'll get 2 trues. And then when I subset, life will be good. This named thing will actually only give me the first element back, okay? Because that's actually typically what happens is they're unique, but not always. And you have to actually know what you're dealing with and what you want back. Do I only want the first one back, or do I want all values that have a name equal to this value, okay? Anyone happy? So integer positions, negative positions, logical masks. How long should this true and false logical be? You'd say you want it to be the same length as X. What if it's not? Well, let's just change the game a little bit. Okay. X is greater than mean of X, median of X. What's this give me?
Will you one vector of the size of the values that are greater than that?
What it's going to do is, this is just, you got to know why this happens. You got to be told it happens. What it actually does, and this is a very, very good way of thinking about it, because this is conceptually what happens under the hood in R. Let's go back. I'll deal with this in a second, okay? Let's go back to X is greater than the mean of X. This is conceptually what happens. Here's my vector of x. Here is my vector of means. Okay? These things have to have the same length. Okay? We just repeat this to make it the same length as this. This is called the recycling rule. We take the smaller vector and we change its length using essentially the equivalent of the rep function. We say rep this guy to have the same length as this guy. So that's fine. So we get, and the mean here is 0.2, 0.2, 0.2, 0.2, well, that's what I did. That's what we just did over here. It goes through and compares this to this, this to this, this to this, this to this, okay? And that's what I said it does. And this is the way R does it. It doesn't bother actually creating this huge long vector for no good reason. But conceptually, this is what happens. So now we're in a position we know what happens over here, okay? So this guy here is of length 2. So we repeat this. This is length 10. So we, okay, 2, 2, okay? And one more, okay, they're the same length, trust me, okay, okay, and now we compare each element. So now we're comparing this element to the mean, the second element to the median, the third element to the mean, the fourth element to the median, and now all hell breaks loose, okay?
So is it going to create a vector that's double the size of the...
No, this is of length 2, this has to be of length 10, so therefore we need 10 elements in this thing, so we just say, repeat this, then repeat it again, and if you're lucky, if this is what you mean, and a lot of times we mean this, okay, because this is kind of what happens. We're in the degenerate case where there's just one element, or oftentimes we're saying x is greater than y, and these are the same. So they're the same length because they were computed the same way, and this makes perfect sense. This recycling rule is actually very useful, but sometimes it isn't. And if you're lucky, so if this was length 11, we'd be in good business. We'd be in business, because this would come out and say, okay, I need this to be of length 11, so I get 2, 2, 2, 2. Okay, I need one extra. Okay, I'll give you one extra, and I'll drop it. So we'll actually get the mean down here, and we'll drop the median off, and R will issue a warning. It'll say, I think you're wrong. Okay, and this raises another issue, which is whenever R issues a warning, it's not a warning. It's an error. Okay, it's just being polite. Okay, okay. There's only 2 occasions when it actually issues a warning that you can actually ignore it. One is when it says there's no new line at the end of your file, and you go, shut up. Okay, I know this. Okay, and you can tell R to be quiet about that if you care about it. It basically says, the reason for this is sometimes files get written, CSV files or something get written. You run out of disk space or something happens, and it leaves a half-empty line with no new line. We're just signaling you may have a problem. It's not actually a problem, but it could be. So you can, if you know that that's not an issue, that's okay. And you'll also see another warning that says closing unused connection. What's a connection? It's a way of reading from a URL or from a file or something like that. We'll close it for you. Much better practice to close it on your first, so you should close it. There's a good idiom for doing all this sort of stuff. They're the only 2. Any other warning, it's an error. I've never seen any other warning come out of R that hasn't actually said, you've really got a problem. Okay, but it could be correct, but we think it's wrong. Okay, but this is this recycling rule, and it's very, very powerful. Okay, it's also, you got to be careful about it, but this is conceptually what's actually happening. Remember I said this is a vectorized language. This is a vector. This operation is going to do element-wise operations. Therefore, we need a corresponding vector the same length. R is smart enough not to actually do this, to actually make this. So if this is a terabyte big, it's not going to go off and repeat the mean, that many times just for fun. Okay, so that's good. Okay, so we've got subsetting, vectorized operations. What's this do? X square bracket, square bracket. It's not the same as 0, because why would it be the same as 0? Okay, it's not the same as putting a 0 in here. What is X square bracket, square bracket? So this is letters. This is letters with this. So you're going to tell me that you're going to tell me, Duncan, you're wasting my time. Okay? We have another way, a longer way of doing exactly the same thing. Isn't that useful? Okay. It is actually useful. Okay, here's MT cars. Okay, I'm jumping ahead quickly. Here's MT cars. It's a 2-dimensional data structure. Okay? Now, again, the logic, again, we like a consistent language. Okay? We can subset in 2 dimensions using exactly the same system as subsetting in 1 dimension, but in each dimension. The same rule applies to each dimension. So this says, give me the first column by position. Okay, position, the first rule we had. Give me the column number 1. What does this mean? I just told you. It means give me everything back in that dimension. If I didn't have that rule, if I didn't introduce that rule like I just did with letters, square bracket, we wouldn't know how to say I want them. I'd have to say 1, 2, 3, 4, 5 up to the number of rows, and I could do that, but why bother? So we do this, and we actually get this back. Uh-oh, I've broken my rule. This is convenient, but I broke my rule. What rule did I break?
The type of object that you got.
The type of object should be, I said single square bracket should give me back an object of the same class as empty cars, which is a data frame, okay? Okay, and it certainly ain't a vector. And I told you, not that none of you should remember what I said. Vectors print like this, so I know it's not, okay? So if I just say, what's the class of this? Okay, let me cheat. I'm gonna get my rule back again. I'm gonna ask for 2 things. Thanks very much. Ha, there we go. Now it's a data frame again. Okay. So what R does here is it says, and this is okay.
It said that data frame is actually a list.
I'll get there in a second, but yes, it is a data frame. I'm not contradicting myself. The class is data frame. Its type of is list. Okay. So this just a moment ago gave me back a vector, but now I said, yes, I know there's only 1 coming back, but I'm saying don't drop the dimensions. Okay, give it back to me as a data frame. So it is actually now obeying my rule. So I can force this if I so desire. Again, why would I ever want to do this? The reason is because if I do the following, when you're writing a function, if you compute which columns to get back, and it happens to just be 1 in this circumstance, you'll end up with a vector back, not a data frame, and then your code will continue on as if it's a data frame, and you'll go, oh, good grief, all bad. So instead of it being a 2-dimensional structure, and you're talking about columns, it's now turned itself on its side, and now you're pulling out columns of length 1, and your code is completely broken. So,
the naming information, right? Because when you just got the record back, you didn't have all these car names.
So these are row names. These are the observation names that are on a data frame. We lose that absolutely. Okay, we can recover that in different ways. We can always get there from, we could arrange the computations to protect this. But this idea that square bracket always gives you back what you want, okay, is important. It doesn't always, because sometimes it's extremely convenient to get this back, but we have this option. There is this other thing, okay, I'm just going to go very quickly, and we can talk about this again on next Tuesday. I'm more than happy to, I like revisiting stuff. Okay, this is where are we? We're now into 2-dimensional data structures, which is fine. Where are we? I told you about the empty thing. I told you we don't need it for single vectors. Oh, we do. We do need it for this. Okay, so I'll give you the other motivation for this. X equals 1 through 3. Okay, there's X. Okay, and I want to change the second value. So we can subset to change a value. Exactly the same rules. Everything I just said over here applies when we put it on the left-hand side of an assignment. So if I say X of 2 equals 10, everybody's happy. If I say X of 1 and 2 equals 100, everybody's happy, okay? Life is fine. I'm just changing the positions. I'm subsetting, and then I put these values in. By the way, here's the recycling rule in action again. It creates an object of length 100. So if I actually did something like the following, what would actually happen? X of 1, 2, and 3 of this and minus 10. What's going to happen? 100 goes to the first one, minus 10 goes to the second one, and 100 goes to the third one. Okay, recycling rule. Okay, so that you do actually have to know it. Okay, here's my warning. It goes, I'm not sure you know what you're doing. Okay, so it's probably not good, but sometimes can be useful. Okay, how do I change every value in X to be 0 or 10 or pick a number? Okay, how do I change every value? Easy. Yep. Happy? No. That's changing x to be the vector of length 1 with value 0, not changing every element in the 3-element list or vector to be 0. That's the other reason I need this guy here, which now says, remember, it says give me back everything. So the empty subsetting says, I mean everything, thank you. And this will actually do what I want, okay? Now, yeah, I'm going to go, okay? I told you about lists. I did actually tell you about lists earlier. It's an ordered collection of things, of anything. They can be arbitrary types. A data frame is a list, but it's way more than a list. It has a massive constraint on it. Okay, 2. One of them is every element has to have exactly the same length, because these are supposed to match up for observations. So you can't have 10 observations in one vector and 3 observations in the other, because we don't know where they match up to, okay? So they have to have the same length. If they don't have the same length, and you assign something in, R will use the recycling rule to repeat this thing to make it have the same length. If you really screw up and it says, I can't do that, it'll stop. But a data frame is a 2-dimensional data structure. Okay, you can think about it. The beauty of a data frame, so how many of you have seen matrices in R? Why? I hope you were doing linear algebra. I hope you were doing linear algebra. Okay. The trouble with a matrix, okay, is how is a matrix constructed? Okay, there is no type matrix in R. It's actually a vector with an attribute. I told you about these names and things. It's a vector, a flat, long vector with a dimension attribute on it that tells me the number of rows and the number of columns, and the number and the values in the vector are organized column-wise, just to piss you off, okay? Because they always think the wrong way, but this thanks to Fortran, that's the way we work, okay? So this is fine, but the problem is what does that? I told you it's a vector. It's a logical, an integer, a numeric. That means they all must have exactly the same types. A data frame, for data analysis, we need to be able to have real valued numbers. We need to have categorical values. We need to have dates. We need to have different things go in, so we need a data frame. And generally, unless you're doing linear algebra, the only time you ever see a matrix in R is by accident, when you do sapply, and it's got multiple responses for each element, and it collapses it down to a matrix. It's nearly always the wrong way around, so you have to transpose it. But so we want data frames. Data frames have 2-dimensional subsetting. Again, the simplest way I can think of for 2-dimensional subsetting is subset the first dimension, and then get the answer, and then subset the second dimension. If you think that way, it all works neatly. So you're subsetting the rows by logical values, negatives, positions, and then you take that answer and then you subset the next guy. That works, but we do it in pairs. We can do it all in one go, where we basically say empty cars of 1 through 3, and then minus 1 and 4. Okay, so we're just now we combine them. We do them together, but conceptually you can actually break it up into leave this guy out and then put this on the other side as being give me back that in 2 separate operations. That's good. But this is the one thing that sometimes is slightly curious. We also do this. Let's do this. Well, actually, let's do this. Here's a list. A equals 1, B equals, let's just for fun, this is 2 to 3, and then this is C is equal to R norm of 5. Okay? If I used, what would happen, by the way, if I did this? Would this be the same? This would unravel them all, and I'd get something of length, whatever it is, 8, 9, 8. Okay, so I need a list. So X being a list has got 3 elements here. Okay, so X of 1. What will this give me? I tell you things and you don't listen. It'll give me a list because it's a single square bracket operator, and by definition / convention, for most of the time, I'll get an object of the same class as X, which will be a list with just 1 element. Well, this is really annoying. How the heck do I get the thing that's in the list? So this is the difference between double square brackets and square brackets. Okay, X square bracket, and then double square bracket, so they always have to be paired together. Okay, this says give me back the element that is in that position. Okay, so that's great. Okay, and I can do this. Can I do that?
There's no element position.
It's like, give me back the one element that isn't in that position. That doesn't make sense. Okay, okay, so that doesn't make sense. So we have slightly different rules here. Can I do this?
Not for this particular example.
No, not for this particular. This is some idiot put this in the language. So what this will actually do is it'll do them successively. It'll actually do this. Go get me the first element, and then go get me the second element of that first element. And if it doesn't exist, you're in trouble. Okay. So in this case, what would we get back? Any guesses? Okay. It says that it's smart enough to actually say this is probably not a good idea. Okay, so this is fine. So what do I do this? I can also do this though. Actually, let me just go back and just do one little thing. ABC, DEF. Okay, we'll do that. So what if I do this? What do I get? ABC. Okay, I get the first element back. What if I do AB? I told you about argument matching doing partial names. It's very convenient when you're typing to use partial names. It's a bad idea when you're programming long term. Again, typically we're not going to be typing ABC. We're going to actually go off and doing some computations that figure out which column we want or which element we want. But notice this. It actually gave us back null because that thing doesn't exist. But watch this, because this gets everybody. Okay. What does ABC? ABC gives us back that. This is just a convenient notation. What does AB give us back? The same thing. The $ does partial matching, but double square bracket does not. You got to remember that. And it doesn't give you an error. Okay?
But only in lists.
Hmm?
Only in lists.
Only in $ does not work on a vector. The double square bracket works on a vector. It's overkill. Okay? Because it says you give me back. We need the double square bracket to differentiate between a single square bracket for a list, because if I say x square bracket 1 of a list, that says give me back a list with the first element in it. But in a vector, an integer vector, logical vector, if I say x square bracket 1, it gives me back an integer vector with only one element in it, which is exactly what I want. But this is where we actually need a slight difference. Okay, but so this is good. But now let's do this. Var equals AB. So therefore you would think that x $var would do what we want. Yeah? Now watch this. Okay? It doesn't, because it doesn't evaluate this. It treats this as a literal. So it's going in and looking for an element named VAR. Okay? So this guy up here, if I type in x, if I say var equals ABC, and if I type x of var, this uses the typical evaluation rules we talked about last day and the beginning of today. It goes and evaluates var, which gets its value as ABC, the string ABC, and then goes off and tries to match that into the names of x, and life is good. Okay, so there are these weird oddities. So you better know what you're looking for, and if you're going to code it like this, it better be there. But it's convenient for you to be able to type this interactively. Just say, oh, you know that column with a really, really long name? I'm just going to give you the abbreviated version, and it works. Okay, so this is when you actually really know what's in there. You use this thing when you're actually going to compute which elements you actually want back. Okay.
Can you also do x square bracket 1 and then an empty square bracket, and that's just
so x single square bracket?
Single square bracket 1 and then another square bracket.
Like this?
Yes, just after that.
How'd
So
you,
you give me that, and then I'm saying give me the.
like this?
Yeah, yeah, sure, leave it. That's more than I had in mind, but okay.
It's the same thing. It's curtains. Okay, let's go back to the logic of this. Square bracket, I mean, I can actually go through and you'll see how this is an infinite chain that we will get the same answer over and over again. You go like, okay, this thing here, okay, just this guy, will give me back a list with the first element in it. this guy will give me back a list with the first element in it. And this guy will give me a list with the, oh, good grief. I just, so the analogy I use is you have a bag, okay, that's your X. It's got 3 things in it. You're asking to get another bag back with a copy of the first element in it. And then now you're asking for another bag with the first element of that bag in, and you keep getting bags all the way down, and you go like, you know, I just want the thing in it. And that's where you have to use the double square bracket or the $sign. There's no way of actually creeping it. And that's because of this logic that says square bracket will try very hard to give you back an object of the same class as X. Okay, that's why it's weird. Yeah, it's annoying. And so I'll see you guys on Tuesday. If you have any suggestions as to what you would like me to cover or anything like that, please email me. And if you see any, I happen to see in my emails, people are saying there's broken links and stuff. If there's any things in the notes that needs more clarity, i.e. links to real documents, or things that are ambiguous, I would really like to actually see them, please. Okay, so have a good weekend. Yes.